distance and this one's this one was there. Yeah, Mr. Right. Yes. And if you give it a moment, usually, yes, well, you have to do that. You may need to disconnect and reconnect it, in my experience, after doing that. Oh, no, never mind. Beautiful. So Igor Klobanov is the session chair. Okay, so I'm just here in my capacity as tech support. You will want to mic yourself up and have fun. I'm going to do the bringing about. Okay, I'm saying this is a regular. Yeah, we turned off the light. Let me double check, but I believe so. Yeah, 30 minutes.
Okay, well, welcome to the afternoon session. Our first speaker is Theo Jacobson from here, and you'll see the title.
Yeah, thanks. Let's see. Is this loud enough? Is that okay? I feel like I'll be turning a lot this way. So. Okay. Okay, so thank you for the organizers putting together this workshop. It's nice to not have to travel. So thanks also to the people who traveled a long way to be here. Yeah, I know it's a confinement workshop, and I'll be talking about Chern-Simons theory, Abelian Chern-Simons theory. So this is, of course, a deconfined theory, but I hope to say something about confinement at the end. So this is based on a recent paper with Tin. So of course, Abelian Chern-Simons theory is ubiquitous. It shows up in a lot of settings. You know, in the study of topological order in 3 dimensions, the theory of edge modes in condensed matter physics. It shows up in, you know, the parity anomaly, the chiral anomaly. It also plays a prevalent role in dualities, and also somewhat recently in the construction of these non-invertible symmetries in 4 dimensions. And the list goes on. But at the same time, you know, it's a very simple theory. The action in the continuum is just A wedge dA. Maybe it's deceptively simple. And it has no non-trivial local dynamics. So this is just a theory of topological Wilson lines, which are just modeling, you know, anyons. And naively, such a topological theory doesn't need a UV completion. So you might be wondering why do we want to put this theory on the lattice? Okay, so why discretize Chern-Simons theory? One answer is just, you know, any quantum field theory, you want to have a setting where everything is finite and unambiguous. But especially for Chern-Simons theory, there are certain subtleties of the continuum theory that we'd like to better understand. So things like the framing anomaly, the fact that monopoles have electric charge, they're not gauge invariant, and even something like level quantization, which is, you know, a very simple thing. We want to see this on the lattice. And we're not the first people to think about Chern-Simons theory on the lattice. So there's a literature that dates back to the late 80s, but most of this literature basically ignored global aspects of the theory. And in our opinion, these are like the most interesting features. Okay, this is a theory which has no local dynamics. So the global aspects are basically all that's there. So we really want to distinguish, the fact that we're doing U1 Chern-Simons theory and not R Chern-Simons theory, for example. And in terms of applications, one obvious thing that comes to mind is in establishing exact dualities on the lattice. So particle vortex duality started off as an exact lattice duality. And then, in the years since, the late 70s, there have been many more dualities in 3 dimensions, some that relate bosonic and fermionic theories involving Chern-Simons terms. And it would be nice to try to use this formalism to establish these dualities as exact dualities on the lattice rather than infrared dualities in the continuum. And finally, it's interesting because it's not obvious that Chern-Simons theory admits a lattice regularization. And I think there might even be some lore or some belief in the community that it can't be done. So what's just one reason why this is not so trivial? One of those reasons is the need for framing. So the simplest correlation function we could look at in Chern-Simons theory is a 2-point function of Wilson loops. Okay, and it's given in terms of this Gauss formula for the linking number. But crucially, in this sum, we have to sum over I and j, and in particular, there's a term where I is equal to j, and we have to make sense of this linking number formula for this curve and itself. And that's not well defined, it's ambiguous. So we have to regularize this somehow, and this is usually done by some point splitting procedure. Okay, so we start with our contour, and we just define this sort of push off. We turn this ordinary line into some kind of ribbon, okay? And this is called framing. So obviously, depending on how one chooses to frame this line, one will compute a different self-linking number. And that self-linking number is just declared to be equal to just the ordinary linking number of like the 2 edges of this ribbon. Okay.
Mustn't stop you from unrelevances. When you continue stuff, I mean, you cannot put it through, right? Without breaking. You can do it without breaking.
Yeah, so if this sort of pushed off loop winds around, you can't remove that by some continuous deformation, right? So yeah, that's true, and you'll just compute a different linking number. So that's just some scheme dependence. That's right. Yeah. Oh, okay, good. So there's a question of whether you can reproduce this, right, in a lattice theory where it seems like, oh, you don't have a continuous. Yeah. Okay. Perfect. So we'll see exactly how this comes about. Okay. So yeah, one might be wondering how can this be reproduced on the lattice? Whether it can be reproduced, and the answer is yes. Okay. So just to set the stage in some notation, we're doing just Euclidean lattice gauge theory. Okay, and we work on a cubic or hypercubic lattice. Eventually, I'll talk about 4 dimensions. And we just take a periodic lattice. So we have sites, links, plaquettes, cubes, hypercubes. And I'll refer to fields which live on sites as 0 forms, fields which live on links are 1 forms, 2 forms, etc. And D is just the exterior derivative on the lattice. Okay, so d phi, if phi is a 0 form, that's just giving you the difference of phi on the 2 endpoints of the link. For dA, you just have this signed sum of link variables going around the plaquette and so on. Okay, so at the heart of this construction is this modified Valon formulation of abelian gauge theories. Okay, so in the usual Valon formulation, we don't use group-valued link fields, we use algebra-valued link fields, but they're supplemented by some integer-valued plaquette variables, okay, which I will sometimes call Valon variables. And in addition to the ordinary 0 form gauge invariance for this gauge field, so A going to A plus d lambda, where lambda is real, we also impose discrete 2 pi gauge redundancy. So we can shift A by an arbitrary independent 2 pi, multiple of 2 pi on each link. And this Valon variable n is just the gauge field, the discrete gauge field for those discrete shifts. Okay. So this is realizing A as a U1 gauge field where U1 is understood as R modulo 2 pi z. And just as in the continuum, we have a quantized magnetic flux. We just have to add up the values of these plaquette variables and all the plaquettes in some closed surface. And it's just manifestly an integer. And in this construction, a monopole is some field configuration where dn is non-zero for some cube on the lattice. So that indicates that there's some monopole at the center of the cube. The modified Valon formulation is just where we set all of these cube, we just set dn to 0 for every cube. Okay, so we just eliminate monopoles completely from the theory. So in one way or another, this modified Valon formulation was sort of discovered either in the 90s or a few years ago. So Igor and David Gross thought about these kinds of constraints in the context of 2D theories, where they wanted a theory that had some manifest T-duality. And similarly, in these more recent constructions, these constraints really sort of give these lattice theories properties that previously only their continuum limits had. So things like their symmetries, anomalies, and dualities. Okay, so there's been lots of work using this modified Valon formulation. And when n is flat, then we can just think of n as being like a representative of the first Chern class in the continuum. So we can have a non-zero magnetic flux through some non-contractible 2-cycle. Okay, so now I'm going to start building up this lattice action. So the naive thing that we could do is we take a wedge dA and we just replace wedge by something called cup. So cup is just the lattice analog of the wedge product. Okay, so it takes a P form and a Q form and gives you a P plus Q form, and it satisfies some Leibniz rule with respect to exterior derivative. Okay, so how do we think about this cup product? Here I'm just showing an example cup product of a 1 form and a 2 form. So if you have some link on the lattice, it's naturally associated with a dual plaquette, the dual plaquette which it pierces. But we want a product between a link variable and a plaquette variable, both on the original lattice. So we just have to translate this dual plaquette shift it over to the original lattice in some direction. And so, for example, we can shift it in by half lattice unit, positive x, y, and z direction. And that gives us a product between this link and this plaquette. And then summing over the 3 directions, that gives us the cup product of a 1 form and a 2 form. Okay, so I just want to note that these cup products break lattice rotational invariance because I had to choose a particular direction with respect to which this product is defined. So if we were just doing R gauge theory, we would be done. This would just be the lattice action, but we're really after U1 compact Chern-Simons theory. Okay, and also at this stage, K is just some coupling constant, which will be fixed in a moment. Okay, so extending this to the U1 case, we need a new ingredient, which is so-called higher cup product. Okay, so unlike the wedge product in the continuum, the cup product is not graded commutative. So you take alpha cup beta, that is not equal to plus or minus beta cup alpha. Instead, you get these correction terms that involve these higher cup products. And similarly, if I took the cup 1 product of alpha and beta, that would be the cup 1 product of beta cup 1 alpha plus correction terms which involve the cup 2 product and so on. So these cup I products take a P form and a Q form and give you a P plus Q minus I form. And I think, yeah, they were first constructed in the 40s by some algebraic topologists on triangulations. But they were only given the nice sort of systematic combinatorial construction on hypercubic lattices a couple of years ago. Okay, and this is actually a physics paper. So these cup products, they're quite complicated. If you look at this paper, it reads more like a math paper, but they have a sort of simple geometric picture associated to them, and they have to do with intersections. So let's consider the sort of generic point-like intersection in 3 dimensions. That's the intersection of a line and a surface. So here I consider a line piercing a surface where both of these live on the dual lattice. Okay, and then I perform Poincare duality. So I define a 2 form, a plaquette variable, which is going to be non-zero precisely on the plaquettes which are pierced by this line. And then I define some 1 form, which is Poincare dual to this surface. So it's non-zero for all of the links which pierce that surface. And then the cup product is non-zero precisely on this cube that encircles this intersection point. Okay, so that's the interpretation of the cup product. You get higher cup products when you consider sort of non-generic intersections. So here I have a line which pierces this surface, but it goes parallel to it for some some distance and then it goes off. And precisely for the plaquettes, which are pierced by these two lines, we find a non-vanishing cup-1 product. Okay, and similarly, we could have a non-generic intersection of two lines in 3 dimensions where this cup-1 product would be non-zero. And similarly, we could consider different, more complicated or non-generic intersections, which would activate these higher cup products. So hopefully this gives you an idea of why these don't occur in the continuum, because in the continuum, we can always resolve these non-generic intersections as just ordinary intersections. Okay, so here's the lattice action. This is just the naive lattice version of A wedge dA. We have some terms involving the Valon variable, and then we have terms involving dn, which have to do with monopoles. So I'll get to those in a second. And these are just the sort of building blocks of this action. Okay, so what about level quantization? Yeah, we set the monopoles to 0 using a Lagrange multiplier. Okay, yeah, I'll get to that in a second. Yeah. Okay, so the action, okay, well, first of all, we want the action to be invariant under ordinary zero-form gauge transformations and also these discrete one-form gauge transformations. Well, when we do this shift, the action is not quite invariant. Instead, it shifts by an integer multiple of k pi I. Okay, but that will leave the exponentiated action invariant, provided k is an even integer. So that's level quantization. If we want to do odd levels, that's really a spin TQFT. And so to do that in an intrinsically 3-dimensional way, we have to involve the spin structure in some way. Yeah. Yeah, it's an yeah. You can easily find. No, but you can easily find this is not like an even integer. You can easily find a configuration for which this is it's equal to 1. Yeah. So from now on, I'm just going to take k to be even. Okay, so now monopoles. So it turns out that these first two terms are not quite invariant under ordinary gauge transformations. They're only invariant provided dn is 0. So only in the absence of monopoles. But that's not a problem because we can just remove monopoles with a Lagrange multiplier, which implements this as a constraint. So that's what phi is. Phi is a 0 form. It lives on sites, and it just sets dn to be 0. Okay. If we want a monopole, we just have to put it in by hand. So we just insert e to the I phi at some site. That's a monopole operator. So it just tells us that now we have magnetic flux going through this one cube and 0 everywhere else. Okay. So I just told you that these first two terms are invariant under ordinary gauge transformations after we set dn to 0 by integrating out phi. We can also keep phi around provided we assign it an appropriate shift under gauge transformations. And that implies that the monopole operator actually picks up an electric charge. Okay, good. This term. Yeah. So this term involving cup 1 is there so that we can assign phi a local, just the usual shift under gauge transformation. If we didn't have that term, it would be sort of non-local, it would be split. It would be split between this side and this side. Yeah. Okay, so monopole operators have electric charge, and that's a well-known fact from continuum Chern-Simons theory that goes back to like mid-80s.
By the way, just a comment, the reason why split is precisely the second term, which is A cup and cup A, and they don't.
Yeah, you can see this A cup 1 dn is like a little Wilson line that spreads out. Yeah. Okay, so what about framing? So it turns out that framing is tied up with a peculiar invariance of the action under these sort of staggered shifts. So the action is invariant if we shift A by some epsilon, where epsilon is staggered in this way. So this link which we shift by minus epsilon, the link which is translated in one lattice unit in each direction, we shift by plus epsilon, and then minus and plus and so on. We have this invariance under these staggered shifts. Okay, these staggered shifts are the origin of some extra 0 modes on the lattice that were noticed in the older literature. But people in these older papers, they saw this as a huge flaw. They saw it as a problem. It made canonical quantization more subtle. And I think people were worried that these 0 modes would somehow contaminate the correlation functions of this theory. But that turns out not to be the case at all. These 0 modes actually perform an incredibly important function, and they're really crucial to the structure of the theory. And now that we've been able to connect these 0 modes to a particular invariance. Yeah, we take, okay, so take an even number of lattice sites in each direction. Yeah, it loops around, yeah. Okay, so we want to view this as some kind of symmetry or some invariance. So we should ask which operators transform, or which are charged and which are neutral. Okay, so the ordinary Wilson loop transforms under the staggered shift. Okay, so we can always choose this shift such that one link in this contour gets shifted by epsilon. And then this gives us an equation, since this leaves the action invariant. We get an equation that says the Wilson loop expectation value is equal to itself times a phase, and therefore it must be identically 0. Okay, so this staggered symmetry actually projects out all of the Wilson lines, no matter how large they are. Even single plaquette Wilson loops are just identically 0. Okay. And really, this is telling us that this staggered symmetry is some kind of gauge redundancy, and it's really projecting out these operators. This was not noticed in the older literature.
This paper,
Static source of thing. Okay, maybe, yeah, maybe they have a statement like this. Yeah. Okay. But if anything, yeah, if that's true, then it was underappreciated.
They did not notice the symmetry, but they noticed that
Okay.
there's something wrong.
Right. Okay. Correlator of 2 Wilson loops will also vanish unless they are arranged in a very particular way. Okay. So what are the operators that survive this staggered symmetry? You can ask that question. Well, if you just put another copy of a Wilson loop down, insert another one, which is just translated by one lattice unit, the 2 phases that you accumulate will just cancel. Okay. So this configuration is neutral. And these operators are the ones that survive. So the non-trivial Wilson loop correlators, you could have a Wilson loop here and a Wilson loop here, but both of them have to be doubled. Otherwise, you'll just get 0. Okay. So this is interesting, but at long distances, these doubled Wilson loops have twice the minimal charge that you would expect. Okay. To get a minimal charge Wilson loop, we have to start with 2 charge 1/2 Wilson loops, but those are not gauge invariant, right? A fractional charge Wilson loop is not invariant under large gauge transformations, so we have to attach some surface that soaks up that large gauge transformation. So this surface is built up out of the Valon variable n. Okay, so this minimal Wilson loop is literally some kind of ribbon. Okay, so we have this little Z2 surface, which is stretched between these 2 charge 1/2 Wilson loops, which are separated by 1 lattice unit. Okay, and this is what the operator looks like. So these first 2 terms insert the 2 fractional Wilson loops, and this term with the cup 1 is what places this discrete Valon variable on that surface. And it turns out that these Wilson loops, these ribbons, are the only operators that survive the staggered symmetry. There are no other operators that are non-trivial. And moreover, they're not contaminated by the 0 modes or the non-zero modes. They actually have exactly topological correlation functions. Okay, so how do we see that? So Chern-Simons theory has a ZK one-form symmetry because it's like a redundancy. It projects out. See, if W is charged under like a one-form symmetry, then only the selection rules that you get tell you that when in the limit that the contour is going to infinity, you need to get 0. Or non-contractible Wilson loops, Polyakov loops have to vanish. But this is saying that any size Wilson loop, even a single plaquette, is just 0. So it's like projecting out these operators completely. Okay, so we have a one-form symmetry. So we can shift A by a flat ZK valued one form. And the Wilson lines are the charged objects, but also the symmetry operators, the generators of the symmetry. So if we turn on some background field, a flat background field for this one-form symmetry, which is Poincare dual to this curve on the dual lattice, that's equivalent to inserting one of these framed Wilson loops on this curve C tilde. Okay, and then the fact that this is a symmetry means we can do background gauge transformations, and those have the effect of deforming this contour. Okay, so we get this topological line operator or ribbon. Moreover, this symmetry has an 't Hooft anomaly. So the path integral is not quite invariant under background gauge transformations, but instead we will pick up some phase and some generic configuration. And that means that in a generic correlator of Wilson loops, they can be topologically deformed, but only up to phases. So if I consider this type of configuration where I have two linked Wilson loops, I can unlink them by doing this background gauge transformation, but I pick up an anomalous phase. And that anomalous phase is just the familiar linking relation for these Wilson loops in Chern-Simons theory. Okay, we can also do a slightly more subtle computation directly on the lattice, and that's of the topological spin. So now let me just consider a single Wilson loop, but which is twisted in some way. Okay. I can untwist it via some background gauge transformation, and I pick up an anomalous phase. And from this anomalous phase, we can read off two things. One, it tells us that this line had a non-trivial self-linking, which was computed with respect to the particular framing which we chose. Okay. And two, it tells us the topological spin of this line. From this phase, we can read off the spin. So the spin of the charge Q anion is just Q squared over 2K. So I actually don't know of a nice continuum computation of this topological spin. Here, we're just able to do it directly on the lattice and just using these background gauge transformations. Why is it the spin? It's like, so if you had a fermionic, so physically these Wilson lines are just modeling the anyons, and putting a twist in the Wilson line is equivalent to sort of taking the anion around it. Yeah. In the continuum, you have to go through the point splitting procedure, and then, yeah, that's right. Okay, so I just wanted to comment on the connection of this Chern-Simons construction to a new form of the 4D theta term, also in this modified Valon formulation. So this first line here is just the naive sort of discretization of F wedge F in the Valon formulation. And the second line involves the monopole. And this last term, again, is a Lagrange multiplier term. So B is a one form, a real one form, and it's interpreted as the magnetic gauge field. So unlike in the continuum, on the lattice, we can have both electric and magnetic gauge fields at the same time. And due to the Witten effect, this magnetic gauge field has to transform under electric gauge transformations with the charge determined by theta. Okay. So this particular form, which makes use of this cup one product and so on, is slightly simpler than some existing constructions where the magnetic gauge field lives on the dual lattice and it has a sort of non-local shift. Okay, so what's the connection of this theta term to the Chern-Simons theory? Okay, so what we do is we set theta to be 2 pi times k, where k is an even integer, and we study this theory on a lattice with boundary. Okay, then almost all of these terms localize to the boundary except for this last one. This last term only localizes to the boundary provided we take this deep Higgs limit where b is pinned to, okay, b is basically exact, so it's pinned to be some d phi. And we can interpret phi as some kind of Higgs field or Stuckelberg field. And because of the Witten effect, phi carries electric charge 1, but magnetic charge k. So it's a dion. Okay, so if we set theta to be 2 pi k, where k is even, and we condense dions, then what we've done is we've actually realized some SPT phase called oblique confinement. Okay, so we condense monopoles, but those monopoles have electric charge. So this is an oblique confinement. And if we do this on a theory with boundary, we exactly reproduce this Chern-Simons theory on the boundary, where the monopole operator, e to the I phi, that phi is the same phi. It plays the role of this Stuckelberg field in the bulk. Okay. And we can couple the bulk to background fields for this one form symmetry, and we get anomaly inflow, all just directly on the lattice. Okay, so just to summarize the construction, we really just discretize U1 level K with K even on the cubic spacetime lattice, but with particular attention paid to the global structure. So we have small and large gauge invariants, we have level quantization, we have monopole operators with the correct electric charge. The observables in this theory are framed Wilson loops. They're literally ribbons. We have the one form symmetry and its a Tift anomaly, which we can use to compute Wilson loop correlation functions. And we have this connection to this new form of the lattice theta term. So I think there are like many worthwhile generalizations and extensions. Maybe I'll come back to this slide because I just wanted to talk a little bit about one of these, which is axion Maxwell theory. So this is something I've been thinking about recently, and I think there's some something to say about confinement here. So what we do is we can take our theta term and just try to promote theta to a dynamical axion. So that's some 2π periodic scalar. So we have we want to have theta shift by an independent multiple of 2π at each site, and so for that we introduce a Velan variable r, which is some integer length variable. So this axion electrodynamics is just described by that theta term, but where now theta is this dynamical axion. We have the same Lagrange multiplier which removes monopoles. Now we can also introduce a Lagrange multiplier which removes axion strings. So an axion string is a configuration where dr is non-zero. Okay, and then in order for everything to be gauge invariant, we also need an extra term which involves some Chern-Simons term and couples to this Velan variable. Okay, so this Lagrange multiplier removes axion strings, but we can put them back in by just inserting some source. So inserting a Wilson surface for the C variable, that will insert an axion string. And then this term here gives us a Chern-Simons, which is flowing onto this axion string. So the axion string is two-dimensional. It's effectively some boundary of this Chern-Simons theory. And for everything to be gauge invariant, we have to add some extra degrees of freedom living on the axion string. And we can actually just do this using bosonic lattice degrees of freedom. Okay, so we can actually have some chiral bosons on the string, which couple to the gauge field and cancel the anomaly coming from this Chern-Simons term. So this is just the Callan-Harvey inflow mechanism on the lattice. Okay, so what about confinement? I think it's an interesting question to ask of whether, well, first of all, what's the phase diagram of this axion electrodynamics on the lattice? And in particular, can we make this theory confined? So if we start with pure lattice gauge theory, U1 lattice gauge theory, at strong coupling, we condense monopoles, we have electric confinement. Okay, that means we have an unbroken one-form symmetry, electric one-form symmetry, and an area law. Okay, now we couple to this axion. This axion coupling breaks the electric one-form symmetry completely, but these authors showed that actually there's some non-invertible one-form symmetry. Okay, so the group-like one-form symmetry is completely gone, but we have this non-invertible one-form symmetry. And in the continuum, this non-invertible one-form symmetry is spontaneously broken. We're just in a Coulomb phase. But now with this discretization, we can ask whether we can force this theory into a confined phase. Okay, so now we ask at strong coupling where we condense monopoles, can we achieve confinement in this axion Maxwell theory? And if yes, that would be a phase where we have confinement which is controlled by this non-invertible symmetry. Now, because of the Witten effect, these monopoles themselves carry some world-line degrees of freedom. So I think it's, this is something that I want to look into. I think it's a very interesting question of what does the strong coupling expansion look like in this theory and whether we can really make it confined. And as far as I know, this is the first discretization of axion electrodynamics on the lattice. So there's no existing literature on this. Okay, so just to wrap up, generalization and extensions. We're currently working on the canonical formulation where time is continuous. It seems like it's fairly straightforward to do this for our Chern-Simons term. Here in the canonical formulation, the staggered symmetry really clearly is some gauge redundancy. So there are some extra constraints that are involved in the canonical structure. And we're hoping that this gives us also insights into lattice discretizations of chiral bosons and chiral fermions. Okay. And then finally, things that we'd like to understand better. First, the odd K theory. Again, this requires some explicit spin structure dependence, and also trying to understand the gravitational anomaly, whether we can see that on the lattice. So that's a sort of subtle aspect of the continuum theory. The framing anomaly, or the need for framing, is really just the symptom of this gravitational anomaly. It seems like it's hard to reproduce on a cubic lattice, but we can sort of repeat this construction on a triangulation, and then maybe there we can see this gravitational anomaly. Okay, so I'll stop there and take questions.
Well, I have a couple of questions. First of all, Am I looking at double Wilson loops again, or can I look at a single?
Yeah, that's a good question. So indeed, in the absence of a Maxwell term, we should be thinking about doubled Wilson loops. So again, we'll have some kind of staggered symmetry. Yeah. And yeah, that's right. Yeah, and similarly here, if we don't add here, I was imagining that we just set the gauge coupling to infinity. We just drop the Maxwell term in the bulk. But with a Maxwell term, we would have an area law for these doubled. Sorry. Let me back up. Absent a Maxwell term in the bulk, also we have this staggered symmetry. And that means that ordinary Wilson loops are just strictly zero. And you can think of that as saying that you had an area law with a Maxwell term where the string tension was g squared, but then you sent g squared to infinity. So all of the Wilson loops sort of went to zero. Yeah, it's analogous to center symmetry. So it acts on Wilson loops just by the discrete phases. Yeah.
I just had a question. Does anything special happen to theta equal pi in this?
Yeah, that's a good question. So I haven't thought about it. So in particular, I haven't thought about how this action, what's the correct sort of parity or time reversal transformation that this action would have, and then maybe that would single out theta equals pi as being special.
There is all this literature on topological insulators, right? Which has to do with theta equal pi and boundary.
Right.
I don't know if you tried to compare.
Yeah, we haven't so far. Naively, so if we really just set theta equal to pi, yeah, there will be some stuff happening on the boundary, but also some bulk dependence. Yeah, I haven't thought about it.
The confined phase, I would guess, is very similar.
Yeah.
I think it probably has the same.
Yeah, it probably has the same mixed anomaly. Yeah.
But,
Yeah, that's one thing I didn't mention is there's.
You have to unmodify it to allow, like to allow.
Well, yeah, we have to somehow we have to make these monopoles dynamical. So either we can couple matter to this magnetic gauge field, and then if we condense the matter, then we'll get electric confinement. Yeah. Yeah. Yeah, it acts on the N2F lines in a non-invertible way. Yes. Yes. Perfect. Yeah, so we need to only condense like charge n monopoles. Yeah, otherwise you lose this. So the presence of this non-invertible symmetry requires at least a discrete magnetic symmetry and a discrete winding symmetry. So we just need to preserve some discrete subgroup. Yeah. Right. So the question is just about chiral fermions, how they arise in this picture. Yeah. I mean, this is a hope, but so one thing is we can study our Chern-Simons theory on a manifold with boundary, and then we find chiral bosons on the boundary. And the hope is that by studying those chiral bosons, we might gain some insights into the chiral fermion problem. Yeah. So they have a somewhat similar sort of canonical structure. Okay.
The theory with the boundary, you have to have something on the boundary to fix.
Yeah.
Very.
So either you say you interpret gauge, you set all gauge transformations on the boundary to zero, in which case you'll find some localized modes, or you allow gauge transformations on the boundary, but you have to attach either some chiral bosons or chiral fermions to soak up that anomaly.
Yeah, so something optional. So when you introduce monopole to
So if you sit down, the continuity.
2 pi periodic. Yeah, it's 2 pi periodic when you, well, in the absence of monopoles. Yeah. Once you have monopoles, then it's really, you only have 4 pi periodicity.
Dense and complete, right? When you set P to P right?
No, so that this only happens when k is even. So if k is odd, then you actually will still have some bulk dependence. Yeah, 4 pi periodic. Yeah. Yeah.
This is, I think, like target of the. But the case is everything.
Yeah, so actually I was a little bit quick. In this axion Maxwell theory, I imagine that I introduce also some coupling, some discrete coupling k, which is an even integer, so that I have 2 pi periodicity of the axion.
I still on this follow might be missing, problems to comment about continuity, right? Because in this way, people speak to them on the latest, the notion of topology is lost. I mean,
Well,
you can jump.
no, but I think if we look at this picture, the 2 ends of this ribbon are clearly linked. I mean, that's some topology that's on the lattice. Right?
Yeah, but it's like a hint between these two spaces or whatever. You see, you can introduce a future jump at the distance which is also more continuity, right? So someone should in your approach should evaluate that it's kind of nothing changes in the size of the latest size. Right?
So maybe one answer is that in this Valon formulation, the topology is sort of put in by having these discrete fields. Okay, and absent those discrete fields, so Yuya is going to talk about how this works absent the discrete fields in his talk later this week. So how do you put the topology back in the lattice? Yeah.
Okay, so I think so. So since you import the monopole response term to that particular, yeah, so correspondence. But also you have data on the links which are gauge fields, and then you supplement them with some data on pockets which show you the flux, the integer flux, the flux to the pocket. And then when you move these things as to move both of them, you can still preserve some.
Yeah, but you are not allowing to go into the gap, right? Because you still like the size, right? You can say, the case will go through.
But it's sufficient to, I think, capture everything.
It's suppose you take just compact QED in 3 dimensions, not Chern-Simons, and put in this zero monopole constraint. Does that make the theory completely trivial, or?
So it's I mean, it's you lose the linear potential. You just have some log.
Becomes free. Or?
Yeah, so you can dualize that theory to a compact scalar. Yeah, maybe. But yeah, so you can dualize that theory to a compact scalar where now you have a no vortex constraint.
I think they did look at this type of model.
Yeah.
What about non-abelian? Can you use
Yeah. For that, no, and I don't know how to do it using this Valon approach. So I think Yuya is going to talk about how to define topological charge in SUM theories. Yeah, for Chern-Simons it's a little more difficult. I mean, something we have U1 level 2, and there's a level rank duality with SU2 level 1. So if you believe the level rank duality, which really there are some subtleties there, then we can do that one non-abelian case. But I think it would be very satisfying to have a non-abelian construction where you could also verify level rank dualities on the lattice. Yeah, okay. So there are some things you can do where you have multiple U1 factors and then you gauge like a permutation symmetry, discrete permutation symmetry, and you can get some non-abelian Chern-Simons that way. But those are discrete. I think those are discrete non-abelian Chern-Simons here, yeah, or finite group.
Okay, well, if there are no more questions, let's thank you again.
How will you know?
Yeah.
I'm gonna ask this in front of everybody.
Okay.
It's stupid, but this went to Greek page number 14, I think. The twist. Yeah, what did you do? No, this one.
this
No,
one?
the next
No,
one.
this one.
This one, yeah.
Okay, good.
So you said in words, you said that you're straightening and twisting this
Yeah.
using a gauge transformation.
That's it.
What?
Okay, so
How can you untwist the loop by gauge
Yeah,
transformation?
but-
What are you doing?
so it really is. What did I do? I mean, the thing was that there's no sense in which this line has any twist in the line. It's just a Wilson that's taking its path. Okay, so now we can do.
And he's
So this-
very into
so when we start-
oh, there's Black Rosa.
And then a background gauge.
So the Wilson operator is a product of.
But not, I mean, not quite, right? I mean, so you have really, the actual operator is,
Oh, the actual operator is this.
yeah,
So
this
this
is,
is the
yeah,
operator.
sorry, this is
Okay.
the operator, and
Yes,
this
good.
is just the contour that we
I
use
understand,
to
yes,
define it.
yes, yes. Okay, so this
Yeah,
is the
yeah,
operator.
yeah,
I
yeah,
see, I see, I see. Okay.
Yeah.
okay.
And you can
So-
see that the two edges
Yes,
are twisted
yes, I
around
can
each
see.
other.
Yes, yes.
And
yes.
so when you do the gauge transformation to just remove this little lump,
So
you
your
pick up
gauge
the space.
transforming what?
So, okay, I'm using background gauge transformation, but really, so I'm using the anomaly, right? But I'm doing a Gilliam definition. This is. So if I do this definition, it has the effect of doing background gauge.
Moving this somewhere else?
Yeah, it's
Okay.
moving this path, remove this.
I see. But- This is very different from normal.
That's right.
Yeah, but the next. I mean,
The normal
you
Wilson
would not have
loop
a
is-
self-linking because you can't, but you could.
But the double Wilson loop, sort of, I'm just trying.
Well,
to
it's a topological
my-
theory. Sorry, yes, that's why. So don't think of it as a Wilson loop, think of it as the generator of the one percent.
Okay.
So it's topological and you move it around via background. Yeah, that's where. So for example, if you add a Maxwell term,
Yes,
that will lift this these zero modes, and then you have also ordinary Wilson loops.
exactly. Okay.
But there are topological lines in that
Okay.
theory, which are the
Okay.
generators of the center symmetry, and they will have similar framing.
Okay.
It's kind of.
It's all crystal clear.
It's all great, but yes, but it's amazing that it has so much in it. Yeah, sure.
So presumably like the doubling of the rules and the framing is fixed was in some direction.
Yeah.
So suppose it was fixed by original convention for the top order.
Mhm.
the frame-
Yeah, that's right. Yeah.
And it will not change the self-linking number, so let's say it goes in different direction.
No, it would. Yeah, so the
Oh.
self-linking number is dependent, like it's always computed with a choice of framing.
Right, right.
Yeah,
So
yeah,
here
yeah.
we see it by the.
But wait a
Yeah,
minute,
so if I-
change the topological spin,
No. So I mean, okay, when I say that the Wilson loop has a topological spin, I just mean if you have a twisted one,
Mhm.
then the phase you pick up when you straighten it is this phase.
And that's not
But-
dependent on frame.
Yeah, the fact that this phase that
Well,
you
that
get,
could-
but
that
which
could go-
Wilson loops are twisted and which aren't.
That is
Depends on-
fixed by the convention.
Yeah.
Okay, that's like frame.
Yeah.
Okay. Okay, here just you have like a finite number of
Choices.
Yeah.
Yeah,
it's not like
exactly.
you count, but,
Yeah.
I don't know. All the diagonal directions. Yeah. Okay.
Now, one could try to set this up on a triangulation
Mhm.
where the cup products then are determined by, you have to choose some ordering of vertices and it becomes much more complicated. And
Yeah.
in principle, so the framing dependencies is,
The good thing is that
determined
it's
by-
always diagonal, right? If it would lie somehow in a link, that would be very confusing. Right?
it's always diagonal. And
I mean, it goes like in a direction that you
Oh,
don't have
perfect.
links. in.
Yeah, that's right, that's
if it would be- Yeah, because otherwise, I wouldn't know. Oh, yeah.
yeah. but I didn't expect to have to learn these higher cup products, but yeah.
So what about? Yeah, this is good.
Yeah.
What is it about?
Yeah, it's about telling some people maybe that they okay, but I think there's a lore that like you could start with some theory where a one form symmetry is explicitly broken, and then integrate out the heavy charge matter and land on some effective description and declare that there's an emergent one form symmetry because you integrated out from. And our point is that that's a little too quick, and really there's in most situations, okay, so there are certain circumstances where that's sort of true. But other circumstances where the symmetry just doesn't survive the infrared, the long distance. So if you, in particular, it doesn't act on anything.
There's many limits.
We're imagining long distance limits.
Okay, but suppose you do all of this in a finite.
Yeah.
Integrate all the terms, you get a bunch of Wilson lines, which are winding.
Sure.
Okay.
Okay.
But the distance is, if you're doing experiments, not probing those minor Wilson lines. In some sense, you should have an emergency. Like
But
strings will not break.
Okay, so yeah, no, it's a question of skills. I mean,
Exactly.
but
Yes,
our point is that
exactly,
in a theory that has
Yes.
confinement,
yes,
if you then deform this theory with some
Yes.
charged matter,
yes,
because you have confinement,
yes.
the matter loops want to screen, like everything will get screened. Because the area law is puny compared to the perimeter law term. For a sufficiently large, group, you always get perimeter, there's always screening. And once you have screening, there's no way of detecting the charge of the Wilson loop at long distance. But the symmetry has nothing. All the charges. are screened.
If you're taking anything system.
So there's like a string breaking.
If you're below, sure, if you're below that scale.
Yeah, but we're talking about long distance, meaning
Okay, yeah.
large compared to M, 1 over
Okay.
M, large also compared to
Okay,
scale.
okay.
Yeah.
Then I agree, okay, and that's what you're working on?
That's the main idea, but then there are a couple of ways where you can declare that there is an emergent symmetry.
Okay.
If you didn't have confinement to begin with, if the theory was confined, then this type of screening argument doesn't really work. If you actually don't, it's not really favorable to screen a Wilson particle, and you can detect the charge of distance of one. And another is if the symmetry is involved in some way. That there's other long distance correlation functions that are non-trivial.
But you always looking above this distance.
Yeah, yeah, yeah.
Look at shorter distance.
Yes. That's right, but if you want to say that there's an infrared.
Okay, yeah.
So it's almost true.
Yeah, there is.
The whole is true.
Okay.
Yes, but the thing is, it came from basically getting annoyed with the literature.
I see.
People were totally unclear about what limit are they taking. So there's
Okay, I
large
see.
math, large distance.
Okay, I see.
I agree with this. And we still not confused. It's still
Yeah.
the things we ourselves.
Oh, yeah?
Yes.
Okay.
Yes.
I see.
But yes, in fact, we were hoping
you to other people here to see if you could help us untangle or
You want to
understanding of basic
Okay,
field
I can-
theory.
Give me an example.
Okay, okay.
Well,
Yeah,
okay, so
you know,
take like super Yang-Wilson 4 dimensions, and there's an anomaly, mixed anomaly between the one form and chiral symmetries. You could ask at the level of correlation functions, how do you see the anomaly? You could insert some backgrounds for the one form symmetry, and you make them so that they intersect. So that you activate B wedge beats. And the claim is that the intersection point there of these
Which is
defects,
point-like.
which is point-like, is charged on the chiral. So there's that's like the operator way that you would read off the anomaly. You start with this junction at a point, and it's as a non-trivial correlation function with the charge operator of the chiral symmetry.
It's not that we follow the phrase, but it is
I
a way of thinking about
understand.
So So already in that setting, you could ask, is that a long distance correlation function?
it. Because if you
After
wanna-
all, these
yes.
two defects are, they might be large. I mean, but they're not far apart. In fact, they're intersecting. So is it long distances or is UV sensitive?
And
In
it's
what
very-
sense
yeah.
does this like, yeah,
Can you ask a more physical question?
Well, let me ask.
No, but-
Inserting infinite effects, okay, look at that one.
no, it's not the
Okay.
fact that they're
It's
infinite,
not
it's the
because
fact that
they're
they
infinite, it's
coincide.
because they-
So if you
I
have
understand.
continuous
Yes,
symmetries, then
yeah.
you might have an anomaly which is detected by
The
like a
only way to
contact term.
insert them is that you are really.
No, they could be a finite, they could be a finite. series. That's two. It's some manifold. You're thinking about some fourth boundary. It's fine. You
Yeah.
don't have to.
Yes,
Yes. But even, I think that also like there's a local equivalent if you have a continuous symmetry. You could see the anomaly from some like contact terms in the current correlation functions.
Yeah.
But it's just, yeah.
If you want to phrase it into the infrared physics.
okay, but you're saying that, but the point is that, what happens to the chiral symmetry? Chiral symmetry is not a problem, right? Not a problem. It's if you're having a significant network, you still have a chiral symmetry. Chiral symmetry, it gets enhanced radio one when you.
Let's say you add them with a finite mass, then it's left alone.
Yeah.
That's probably.
Like the same, so.
Yeah, but then, okay,
Exactly.
well,
So
that's
actually the question.
that's
That's
getting
the
into
real
something
physical
even
question.
else, because then you have a baryon number symmetry and you can activate the effective deflux by an appropriate baryon number back. But that,
As you. Better than.
but it's a different vision than the one I was having.
Then we have other confusions. that we have.
Yes.
That's, yeah. Well, there's also the one about you have a trivial gap phase. What should we say about operators, expectation values of operators? What do we expect? Are they all supposed to be trivial? Make them big? I'm actually confused. So imagine you have a some QFT with a trivial, gap. And you insert some operator or a collection of operators, complex. They're not filling space. And let's say you're working infinite law. Certainly the expectation value of like, say you have local operator over here, local operator over here, even if they have a trivial gap. There's going to be some interesting non-trivial thing. But in the limit that you take in part, you have a trivial gap phase, you get support.
Yeah, that's part of the.
Precisely, yeah. So it's just it's a total.
But no,
It's exactly it's total logic. Now you could try to say, okay, well, what if I have 16? And again, if you have a trivial gap phase. Then again, that's comparison. Also minus all that's improved.
Yes.
So is it like, can I say this for any finance or whatever I do? I insert something, maybe it's complicated, but in the limit that I make it thin, but I think it first, you always hold either the zero operator
I mean, do you have something else in mind that it could?
Well, I did until some.
Yeah, so I mean, we were thinking about, like, how do you see if the anomalies from inserting some sort of
Yeah.
operators? And in some cases, it's detected when these like operators are touching each other.
Uh-huh. Yeah.
Well, not even linking, but like in
But yeah.
1+1, you can have like open pi line, alpha line, some other, and
You
then
want to know about the mixed group?
yeah, so there's some phase in this cross, and it can't, if we insert other things, it can't actually trivialize it by subcounting them, so they need to put on. But then we want to ask whether just considering this correlation function that can't have a typical gap phase.
Which they're not really should tell us. They probably should tell us. You can phrase that as gating. Argument for gating. Suppose you're going to give an argument for correlation. All right.
So by
Well, I mean, you can make some like if correlation function is not significant, then I don't have really. That's like kind of like the anomaly.
That's
Like
yeah.
the
Yes. That's what I would.
anomaly.
That's what I would want to say.
What you should do. As long as you can say, like, as long as you have a correlation function, you know, like non-triviality is like.
yeah. Guess we wanted to like, direct, like just starting with this correlator.
Yeah.
Or some correlator of symmetry defects which exhibits the anomaly.
Yeah.
So
this is like some, yeah, I mean, this is like some correlation function that measures some linking invariant in general. I don't mean like, that's.
Linking like.
I guess in particular, this is confusing when you have these intersections. So like if you were doing Chern-Simons theory where when it really is linking, and everything can be like very far apart. And if I imagine flowing to long distances, I think that these operators as being very large and something, they might be linking before. Yeah. And then that just once you have these kind of things, like operator and touching, and it's not exactly clear how you would get this and ask about like the long distance. It just seems like a UV something. Yeah, I don't know.
But you should still be able to make sense.
I agree.
This feels like one is on safer territory.
Yeah, so like in this case.
So you want something sufficient.
So if I like if we put like a compact like on the mixed anomaly of the momentum and bonding symmetry, you can read off from this correlator. Blue is one of the minus. If you have either one of these on its own, then you could choose a counter term that would trivialize the phase. But when you have both of them together, you can't remove all of these. Yeah, mixed anomaly. But now if we imagine that this is not exact, one of the symmetries is not exact, but it becomes on my then you would like to have some state. So though, consider this correlation at long distances.
Yeah.
It should be matched, even if microscopically one is inverse.
Yeah,
But because
because it's the same, precisely because it's like, as long as the symmetry emerges, that's exactly the correlation. Doesn't matter that it emerges. Okay,
Exactly.
that's good.
That's nice.
Yeah. Good. Okay.
But then it seems like, okay, suppose the blues, the winding symmetry. It seems like even in a trivially gap page, we can get this correlator to be and exhibit the anomaly. Because like, yeah.
Because one of the lines is topological. So let's say the black lines are in topological. So you can read off all phases from here by just shrinking. That cannot be some sort of.
But the other line, remember,
The other
Yeah.
line is exactly.
is it up?
Well, I guess that's like part of the question is like, where is the fact that these operating in topological
Yeah.
extremely important for the anomaly matching condition? Like you could just, I don't know, these are just some random line operators that happen to have a trivial correlation. But somehow that shouldn't,
But,
that's weaker than having an adjust anomaly. That's
wait, the sorry, never mind. So, but like if the other symmetry is explicit. Or is that,
Well, it's explicitly broken shortness.
sorry.
By construction, that's a matter of.
But then you want at long distance.
At long distances, you might. Be, but whether it does or not, it might. You know, if you add, if it's heavy, then maybe it's okay. Your density might.
Yeah.
That theory, in fact. And yet this correlator naively, that's, we got confused about it. It seems like even in space. There seems why. That phase have better.
So I guess the crux of the issue is like, if we would be like, like, and like the general IR, all like this. Right, that's kind of.
I mean, I'm also just confused about like in anomaly match. What if you try to view anomaly matching as a statement that you have to view some correlator, where exactly is the topologicalness property? If you could just have some non-topological operators which have like correlation.
Yeah, but then they might not necessarily like throw like an anomaly with symmetry, right? Like, because here I'm looking at like, symmetry operators or operators that are charged for like, symmetry, right? And so like the topological. That.
Yeah.
Position, I guess. I mean, like that's. Like I'm supposing that I'm looking
I think that given the symmetry of I mean, I think we're confused about even like a more basic thing, just like given some symmetry. How exactly do you get to that? Like, what's the argument that goes from here's the anomaly to
You're not happy with just the. Like if you suppose you have a trivial police, then you can gauge symmetry, but then.
Yeah.
Well, that's usually. You know, we want to refer and infer if we are crazy.
Yeah, I guess what I
we take care about this is we want to. In which case, teaching is awesome.
Yeah.
What's the other way? Correlation. Phrases, those might be fine. So we're in a different way of thinking about it. Huh?
That's
engaging with the only way.
But I think.
But then it's
Yeah. For example, in superannuation, we just about the sample defects are not massive fundamentals because these I can end on the massive fundamentals. The close line, no, a close line of the different works. You can break it all. Of those sorts, right? Yeah. On the Wilson lines of the heavy beats. The center symmetry. Think of the lattice or a bunch of blockheads when you do this.
Yeah, no.
Yeah. So you have a yeah. It has to be incomposed. But now you have a fundamental. And like a show, this one does have.
Somebody had to say.
It's not considered people that are a bunch of protests. We add the conform. It's not this. No, it's not, because you said so sorry? Boolean operator is the closed surface. Oh, in 1+1.
The generators of the one from Schwinger.
Yeah, but the one from the transformation.
But we're talking about slightly different.
No. Wilson lines can never.
Yeah.
I know we wrote it.
No, but the Wilson lines are different.
Yeah, you have the background.
Yeah.
You want to consider the.
Yeah, exactly. That's a
That makes-
yes.
That
That's
makes
all I
sense.
was saying. Yes. The fact that these surfaces are topological is the reflection.
No.
No? What do you mean? Yes, of course.
It's the coupling you were saying.
Yeah. Even not even.
Wilson operators.
Yes.
Yeah, those are the generators of the center. Yes, yes.
If you add matter, then they're only approximately. The next question.
Okay, very good, very
And
good.
the next question is, do they have something to back?
So the
In other words, are there some
You're right,
non-trivial
you're right. I was,
operators?
yes, I was, so these guys can ask, okay, that's true. But in what sense are those? What does it mean to be
So it's the
non-reflective?
integrating a whole possible.
I'm still trying lining it up with an operator. You can't move it around.
I was
really.
thinking.
Sure, exactly,
I
yes.
mean, it
Yeah,
has some.
Sure.
But,
Where's the next one?
It doesn't get you the master.
Yeah,
it is.
well, the reason it's
Sorry.
topological is
So we
because
have
like
a
there's a
session
conservative.
I like check.
You're not the session.
No, I'm not
So
the session chair. I just-
the charge doesn't around, but then if there's a.
But it's true, it will be like.
No, it's not.
Because, look, if you say the kind of fundamental, if there is any degeneracy, if you know what you should break it, right? Unless there is some other reason to be degenerate.
Right, but then,
Okay.
like this is there with the. Well, no, just that you can activate some non-trivial. With an appropriate there. And then you might be able to. Make it.
So to see, that's an interesting reason for that.
Cool.
Right, we resume our afternoon session with the talk from Russ Dempsey from Princeton University. We will talk about this work, the current preparation. Joined with me. So I will keep very impartial. Please go ahead.
Great. Yeah. Thanks, Igor. And thanks to the organizers for the invitation. Yeah. So thanks. I'm excited to talk about some. Oh, I'm sorry. Yeah. Let me do that. Yeah. Okay. Does that work? Okay. Great. All right. Yeah. Thank you for the invitation to talk about this. I'm excited to share some fun work with an ongoing collaboration with Igor and Silviu and Ben Sogard and Bernardo Zahn, who are both here on the two flavor Schwinger model. Okay, so first, some overview of why 2D gauge theories are interesting. We've heard about some of them today already. In our community, they form great models of confinement. Confinement is the default behavior in 2 dimensions. The Coulomb potential grows as the separation. And they also have some interesting deconfining transitions when there are massless fermions in the game, although there are many interesting subtleties with that story. And they're a nice model for symmetries, ordinary and generalized, and their anomalies. They're also of interest in the condensed matter community. They form great targets for numerical tensor network methods. These are cases where we have a lot of exact and non-trivial results. And largely owing to the fact that there is no dynamical gluon degree of freedom in 2 dimensions, it can be integrated out, and these models can be represented often in terms of spin chains that are familiar targets for these kinds of methods. And maybe the most interesting thing, which I will not talk about at all, is that these are also experimentally realizable. People using cold atoms and optical lattices can simulate these the long-range potentials that show up in these theories and actually simulate some of these with real atoms. So in this talk, I'll be focused on one of the simplest possible cases, the Schwinger model, which is a U1 gauge theory coupled to some fermions. And there'll be a theta term as well, which I'll talk about at length later on. And so the 2 questions I want to focus on, one is how can we realize it most faithfully on the lattice, which will involve some discussion. And then we'll use that most faithful lattice representation to learn some new things about its physics in the continuum. Okay, so I'm mostly interested in 2 flavors, but I'll start with a discussion of one flavor to build up some of the story. So we're going to build a Hamiltonian lattice formulation. So we'll start with the Hamiltonian. We have 3 terms. One is the gauge kinetic term coming from this E, which is conjugate to the gauge field, and it's shifted by theta over 2 pi. So we should think of theta here as just a background electric field that shifts all the electric fields. And then we have fermion kinetic and mass terms. And very importantly, the gauge invariance implies 2 things for us. One is the local Gauss law that says that this electric field is going to change depending on the fermion number density. There can be normal ordering ambiguities on the right, which I'll come to later. And second, large gauge transformations tell us that these E of x's should be integer valued, but then the effective electric field, E of x plus theta over 2 pi, we can shift with theta. So to put this on the lattice, we'll go back to an idea from Banks, Susskind, and Koget from 1976, which is to take the 2 component fermions and stagger those components on the even and odd sides of the lattice. So we'll have a lattice where the even components, pi 0, pi 2, pi 4, correspond to the upper components of this fermion, and the odd sites correspond to the lower components. And then on the links, as usual, we have the electric field, the gauge field. So let's think about how we can take that Hamiltonian and turn it into a lattice Hamiltonian.
The gauge kinetic term is fairly simple. It turns into a sum of these ln's, which are our lattice operators for the electric field, again shifted by theta over 2 pi. We have a fermion kinetic term, and importantly, we're going to choose the gamma matrices such that the gamma 5 that appears here is sigma 1, such that this term is going to link an upper component to a lower component. And that's something that looks like linking two adjacent components on our lattice. So we get something that looks like a fermion hopping term on our staggered fermion lattice. And finally, the mass term is going to be just represented, since gamma 0 now is forced to be sigma 3 by this choice. We have a minus 1 to the n term, a minus 1 to the n factor in this sum for the mass term. And again, probably most important, the gauge invariance condition. Here's where those normal ordering ambiguities come in. Ln minus Ln minus 1, which is the change dielectric field, is going to be related to the fermion number density, but there's a shift we have to include. And there's some choice here, but we need to have a shift. And so we choose to put it by minus 1 on the odd sites. And so this is what we need to impose on the lattice to guarantee gauge invariance and to have charge conjugation symmetry. Okay, so all that is just to say that the literature, I should have said, yeah, we have some parameter here we put in front of the sum, which you might expect would just be the mass, and in most of the literature it is. We claim that this should actually be shifted by something proportional to the lattice spacing. And the reason for that is symmetry. So we want to preserve some of the anomalous axial symmetry. And so, recall there's this axial rotation, e to the I alpha gamma 5 times the fermions, and it's not preserved in the quantum theory. It has this anomalous current whose divergence is related to the effective electric field. We could write this as a divergence of a gauge non-invariant term, and try to imagine sort of a gauge non-invariant conserved operator. The effect of which, if we look at what this term is, it's epsilon times f mu nu, times f mu nu. So if we try to act with this operator, really what we're doing is adding this term that looks like the theta term. So we're going to end up shifting theta. And so at the end of the day, when we can show that these axial rotations are going to change theta by 2 alpha and rotate put a phase factor in front of our mass. And so this is a well-known continuum story. And for most values of alpha, we shouldn't really expect to see this on the lattice. It would do something pretty funky. But for alpha equals pi over 2, it's rather special. The axial rotation will just interchange the upper and lower components of the fermion. And since we have this staggered lattice formulation, we could really imagine doing that on the lattice by something as simple as just a one-site translation. So one-site translation down this lattice is going to take chi 0 to chi 1 to chi 2, and remember these are upper, lower components. So this is something that looks a lot like what could be the axial rotation by pi over 2. So let's see if we can make that story more explicit. If we look at our lattice Hamiltonian, you could almost imagine, this term is just a sum, and this term is just a sum. These things are going to be just fine under a one-site translation. It's the minus 1 to the n that would seem to be our problem. And we could almost get away with it just by flipping the coefficient of that term. But not quite, because of our meddling kid, the Gauss law, which is not explicitly not invariant under a one-site translation. And so if we want to make this into a symmetry, we have to be sure to preserve this Gauss law for our gauge invariance. So let's do that. So if we now try to do this one-site translation, send the fermions to the next site over, this will change the QNs by a shift of minus 1 to the n. These are related to the Gauss law, and so we have to shift the ln's appropriately to maintain the Gauss law. So we get another shift by 1, in this case on even sites. And now we see what this is going to start to change the Hamiltonian that we wrote before. So the ln's that appear in the gauge kinetic term, because of this preservation of the Gauss law, now need to shift. And we can rewrite that shifted sum of ln squared in this sort of suggestive way, where we now have theta shifted by pi, as we should have for an axial rotation, and then an additional term with this alternating sum of the ln's. If we then use the Gauss law one more time, this alternating sum of ln's becomes an alternating sum of chi n dagger chi n. That's just the mass term. So at the end of the day, what we've recovered is the same Hamiltonian, except for a shift of theta by pi and a shifted mass, which is possibly unexpected.
Kind of the limit A equals 0, right? Terms which are linear A could be added from the very beginning.
That's exactly right. Yeah. So if you're taking the continuum limit of your lattice, you can add anything times A to the mass, and you'll get the same limit. That's right. Yeah. So you will have the same continuum limit. I'm going to show that it gets there a lot faster. You're right. I'll show that in just a moment. Right. So yeah, in brief summary, in the continuum, an axial rotation by pi over 2 is going to shift theta by pi and negate the mass. On the lattice, by following our nose, we've found that a one-site translation has almost these properties, except it shifts the lattice mass, it negates the lattice mass and also shifts it. And so this suggests an identification of the lattice mass with the mass by this d squared a over 8. And right, so this will have the same continuum limit, but it might be improved on a finite lattice, which I'll show in a moment. Okay, so let's do a first test case with sort of a rather simple quantity, the expectation value of the effective electric field in the ground state. So for m equals 0, the continuum axial symmetry sets this to 0. This quantity is just 0. But the lattice doesn't know about the continuum axial symmetry, right? So the lattice can give us a non-zero quantity that in the a equals 0 limit brings back to 0. Restoring this little bit of the axial symmetry takes away some of what could be the dependence on the lattice. We could, for a generic, non-shifted mass, we could have had cosine theta, cosine 2 theta, cosine 3 theta terms when we compute this on the lattice, and we've just killed off alternating terms. So we can see the effect of that now on the lattice. I'll show a couple plots like this, but so this one we've as a function of theta, we've computed this expectation of the expected electric field. The triangles are without the mass shift. And so the gray triangles are for a very small lattice of 4 sites. The darker triangles are a slightly larger lattice of 10 sites. And they are getting there to the right answer, to 0, but they're really taking the scenic route. The circles are with the mass shift. And we can see, first of all, this exact result that it's only a cosine 2 theta dependence and higher, even frequencies that show up. And then even by the time we have 10 sites, we're almost very close to 0 already. So this is a huge improvement over the unshifted model. I should emphasize 10 sites is something you can really simulate on your laptop. This corresponds to diagonalizing a matrix of a few thousand dimensions. Actually not too taxing. And we've graphically improved what that can do for this observable. And if we turn on a mass, now it doesn't have to be 0, but still the circle points that have the mass shift are going to follow the result from mass perturbation theory much more closely. So we've again improved the behavior. And just in case computing 0 wasn't so impressive, we can try to compute this more complicated observable. So from Bosanization on a circle, we have this exact result for the from Hetrick and Hosotani for the expectation value of this mass operator psi bar psi. It's a very complicated expression, but we can just try to see, we can plot this and compare to what the lattice gives us. And again, the triangles are sort of getting there, but they're really still quite far off with these small lattices. With the mass shift, we really track this quantity quite well as a function of the circle length. This is again encouraging for what we can do with the mass shifted lattice approach. Okay. So now that we've finished these sort of test cases where there are exact known results, I want to look at something where we really need the lattice to even have a hope of seeing what happens. So I want to talk about the phase transition for a Schwinger model at theta equals pi. So to motivate this, if we think about the theory on a circle being in some fixed electric field background, we can do some pair creation to shift the value of the electric field by 1. And so we can think of this as sort of descending to a minimizer of the effective electric field squared. That minimizer is unique except when theta equals pi. Then, of course, we can have the plus or the minus 1/2 electric field backgrounds. And so there, you can imagine there might be 2 phases here. One with this very small m, where this same process is going to be fluctuating between these 2 vacua, the plus 1/2 and minus 1/2, two states, plus 1/2 and minus 1/2 states. And so we have a single vacuum. For large mass, though, those fluctuations should eventually freeze out. And so we expect this to become 2 ground states, each with a non-zero expectation value of the squared electric energy density. So something has to happen in between, and we expect there to be a second order phase transition for some critical MC. And a simple question we can ask and try to answer on the lattice is, what is the value of this critical mass? Okay. So this has been asked and answered before without the mass shift. So way back in the 80s, using exact diagonalization on the same order of, say, 10 sites, without the mass shift, Hammer and friends found a critical mass of 0.325 plus or minus a bit. We did their exact same calculation with the mass shift and get roughly another digit of precision. Now it's 0.335 with some uncertainty. A great tool, which I wish I could speak more about, but I'll just, a lot of those details is DMRG or tensor network methods. These are tools developed largely in the condensed matter community, but they allow for extremely efficient extraction of the lowest eigenstates from some of these types of models. We'll think, just sort of a magic tool that lets us go from 10 sites to close to 1,000 sites at the lattice, and so we can do a much better precision. This again has been done before without the mass shift, and there it was shown that the critical mass is 0.3335 with some uncertainty in that last digit. At this point, it is tempting to think that perhaps this is a rational number we all know and love. I'm so sorry, but in one of the greater disappointments of the recent past, we computed this to one more digit of precision and showed that in fact the error bar just tightened around this 0.3335 value, and it is not 1/3. But that curiosity aside, the nice thing about this is that we have an extremely sort of precise way of extracting these critical points in these models. And so we want to see what we can use that for in other cases. Let me just describe that method real quick. What we did in this case is a little bit different from those other 3 cases, although we did it their way as well. But perhaps the most efficient way we've been able to find is to look at the entanglement entropy on the lattice. So we take our one-dimensional lattice of these fermion sites, split it into 2 sections, and calculate the von Neumann entanglement entropy of 1/2. And it's known that if we're at a critical point, right, that this is going to scale universally as the central charge, in this case divided by 6, times the logarithm of the system size. And so what we can do is compute the ground states on the lattice, extract these entanglement entropies for various subsystem sizes, and use that to extract an estimate of the central charge. And so we can see what happens when we do that for the one flavor case. I hope I said before, but these models are this transition we're looking at is expected to be in the 2D Ising universality class, and so it should have central charge 1/2. These estimates actually go well above 1/2 and back down, but this is really a sort of a red herring. What we should be looking for is not the point where they're maximized, but the point where they seem to be, as we increase the number of lattice sites, the point where they seem to be stable and scale invariant. This is the point that should correspond to the critical point. And we see that this is very nicely getting to C equals 1/2 and is near this 0.33 critical value. So by doing this very carefully for many sizes of the lattice and for many lattice spacings, we can extrapolate the continuum value of the space. So those are the tools. Now I want to apply it to the 2-flavor model. And so let me remind some differences between the 2-flavor and the 1-flavor Schwinger model. With 1 flavor at m equals 0, all we have is the Schwinger boson. There's no massless sector. For 2 flavors, we still have the Schwinger boson, but then there's also going to be a leftover degree of freedom, which forms C equals 1 conformal sector, which is given by the SU2 level 1 WZW model. So this is distinct massless theory for sure. A small change in the tools, the mass shift ends up having twice its value, now A/4 instead of A/8, but it's very much the same idea. It restores a notion of the axial symmetry. And the best part is that the axial symmetry for 2 flavors can be made a true symmetry. Right? Before we had to shift theta by pi, so we're really relating 2 different theories everywhere other than the massless point. Here, even away from the massless point, we have, or rather, here we have a true symmetry where we're not shifting theta by pi, we're coming back to the same theory. Let me just recall some known results for theta equals 0 before getting to the interesting case of theta equals pi. At theta equals 0, if we say turn on both masses with an equal mass deformation, this corresponds to perturbing that C equals 1 CFT by an operator with scaling dimension 1/2. And so one can work out from this a scaling of various quantities. That Vev psi bar psi that we talked about before is going to scale as this mass to the 1/3 power. Similarly, the mass gap would be that a mass to the 2/3 power. These things can be worked out, and many of them can be actually seen on the lattice. But like I said, I want to focus instead on theta equals pi, where the phase transition happened before. So let's think about what we know for theta equals pi already. First of all, as we said before, there's going to be a CFT at the origin with m1 equals m2 equals 0, the c equals 1 point. And then we also know that as we take one of the fermion masses very large, we have to come back to the same story we just had before with the one flavor model. So if we say take m2 very large, I'm sorry, the mass label does not show up. This is a plot of m1 versus m2. Sorry about that. So if we take m2 very large, then we should have the same story, whereas we turn on m1, eventually we freeze out these fluctuations between the +1/2 and -1/2 states, and we end up with 2 ground states. And so the gray shaded region here is meant to represent a 2 ground state phase. So we know that we have this, this dashed line, and that roughly 1/3 is going to be where that transition happens for very large masses. And so, intuition and also some work from Holman back in 1976 might suggest scenario 1, where these lines of c equals 1/2 theories sort of have these hyperbola-shaped connections, and that's the end of the story. The reason you might guess that is that it would seem like if you had an additional flavor of a fermion, it would be easier to fluctuate between the two E equals +1/2 and E equals -1/2. And so you'd freeze out the fluctuations a bit later as you turn on the equal mass deformation. So that's one reason you might guess scenario 1. So there's some recent calculations by Howard Georgi of some correlations of fermion bilinears in these models. And it is suggestive of conformal behavior along this equal mass line. And the suggestion was that the c equals 1 point might actually be extended to a line along the m1 equals m2 direction. This seems to be at odds with the symmetry. So the c equals 1 point we know is the SU2 level 1 WZW model. And all the way along this line, we should have the SU2 flavor symmetry of the two fermions, since there's an equal mass. But the only marginal deformation we can make of that SU2 level 1 model is the change of radius for the compact boson. And that's always going to take us away from the special SU2 self-dual point. So there seems to be no way to keep this a CFT while also preserving the right symmetry that we need. Perhaps something a little bit different is going on, but nevertheless, George's calculation suggests something very interesting happens along that line. And so I'll show you some evidence that what we actually see is scenario 3, where these lines bend opposite the way your intuition might have suggested, and actually meet at the c equals 1 point at the origin. So I'll show you now some evidence from the lattice and some also calculations we can do, strongly suggesting scenario 3 is the phase diagram.
That's right, exactly. So that's kind of the dimer, yeah. So they're not, sorry, dimer. I mean, I think, whole scenario 1.
Yeah, I agree. Certainly, scenario 2 is excluded, and scenario 1, sure, there should be some deformation you can make to flow. I couldn't quite hear.
Oh, you mean it goes back? Yeah.
So, and that's a good point. Yeah, so that's the one way you could get around the scenario, except that George's computations show that if it is a CFT, the scaling dimensions of the lowest operator are going to change. So that rules out that case, I think, completely.
No, I don't get the information without the only so if you project that tax.
Sure, quite follow, but in any case, yeah, I agree with you all that scenario 3 is where we should be looking, and I'll show you some evidence now for that from the lattice. or sorry, before the lattice, let me do a quick computation to further suggest scenario 3. So if we take one of the masses very large, we can integrate out the heavy fermion from this action. And what we find is that to leading order, what's left over is the one flavor action plus the shift of the f squared term, because it's minus 1 over the second mass squared. And so the effective coupling is shifted in a similar way. And so this already shows that the phase transition we know from the one flavor model is actually going to be bending the way in scenario 3, where the critical mass is decreasing as we head to smaller masses of the second heavy fermion. So there's one suggestion of this third scenario. Sorry, say that again.
Yeah, there is a G squared.
Oh, I'm sorry. Yes, there is supposed to be a G squared here. Yes, thank you for that. Yeah, this is M2 in units of G, or G squared over M squared. Yeah, thanks for that. But indeed, yes. All right, now let me show you the lattice. So here is a plot. The background is the entanglement entropy I was describing for one particular lattice, some large number of sites and small lattice spacing. And this is the kind of quantity we're using, right, to do that same finite size scaling estimate of the location of the critical point in this model. So the background is sort of one of many such pictures we need to make to eventually get these continuum estimates and the black dots of where a critical point is, should one exist. And it also gives us an estimate of the central charge at those points. And what we find is that all along this nice curve following scenario 3, the central charge comes out to 1/2, and we get these this critical line of 2D Ising transitions. And it nicely follows sort of the curve we sort of expected, and is getting very close to meeting along this diagonal line already by a relatively large mass. So furthermore, if we take that expression for the large mass asymptotics that I just wrote on the previous slide, these points, that's the white dashed line, and these points are matching that computation very precisely. Thanks. So everything seems to be checking out here. We match large mass asymptotics, and we see these lines coming together towards the origin, just as in the scenario I was suggesting. So this is encouraging. Let me show you one more encouraging plot from the lattice. Let me explain this. We are here working with open boundary conditions on the lattice. Open boundary conditions are going to explicitly break the symmetry between the two vacua I was speaking about. So if we take the ground state and look at the expectation value just of the electric field, that should be 0 when we're in the symmetry unbroken phase, and should turn on when we go into the symmetry broken phase. And here we have a picture of that seems to match very nicely what we expect. So we again have this this symmetry broken region with boundaries that curve inwards towards the origin and meeting or coming very close to meeting on a line near the origin. So yeah, this is very encouraging in favor of scenario 3, and is heavily reliant on the mass shifted lattice approach I was describing earlier. And so definitely hints towards something very interesting happening near the masses point, as some people have already been suggesting. And so let me finish briefly by discussing what happens near the masses point. So we said at theta equals 0, if we do this equal mass deformation, there's going to be a delta equals 1/2 operator returning on, and we can easily see some parallel scalings of these quantities, and it's interesting, but not not anything too fancy. So theta equals pi, though, the coefficient of that deformation vanishes. If we take equal masses and set theta equals pi, that operator is not turned on. And so we can ask, what is the deformation here? It's hard to throw this in the last minute here, but so if we bosonize the fermionic theory, this reveals that there's this massive boson, the Schwinger boson, with a mass that's well known. And then the other bosonic degree of freedom is this compact boson that gives us the SU2 level 1 model. And so we can ask what happens if we integrate out this heavy Schwinger boson and see what happens to just this phi minus field that is giving us the CFG sector. And what we find is this deformation by this cosine operator with coefficient root 8 pi. And it's that point at which this operator in the Sine-Gordon model has dimension 2, is marginally relevant, or excuse me, is marginal with the first order. And so If we think then about the RG flow of the Sine-Gordon model with this particular coefficient in the cosine, this has been worked out long ago in the 80s by Amit and friends here. And this is describing the BKT transition. And so what we actually end up seeing is that the mass gap, for instance, near the origin should be exponentially small. It should go as e to the minus 1 over that mass squared. This is a nice prediction of something that's going to be very difficult to see on the lattice. But what we can look at on the lattice is the correlation length going as the inverse mass gap. It's going to be exponentially large near the origin. And so we can try to see if we can match this behavior and confirm this story of a BKT transition near the origin. And in fact, we can. And so, furthermore, this coefficient appearing exponential can be computed from their RG analysis. And what we can do is extract an estimate of the correlation length from the entanglement entropy that we already were looking at, and see how that correlation length depends on this 1 over m squared. The prediction is that it's exponential, and indeed in this log plot we see exactly this behavior of e to the 1 over m squared dependence. And furthermore, the slope, this dashed line is depicting the value a computed in the RG analysis. Our points seem to be headed right towards that slope and doing better and better as we go to smaller and smaller lattice spaces. So everything is consistent with the story being just this way. So I'll finish there just to sum up. This mass shift drastically improves our numerics and it opens up a larger range of what we can study with Hamiltonian lattice theory for the Schwinger model. And these tensor network methods also are essential to doing really precise numerics and using all these tools. We see this strong evidence for what may be a surprising phase diagram for the two-flavor Schwinger model. So I'll stop there. Thank you.
Great talk.
Let's say that we start from n equals 0.
Yeah.
Okay, then we should non-zero value of the mass,
Right.
And I wonder if we should symmetry associated with mass or not, because if you have a shift, then something going on with this. Right?
That's right. Yeah. So right, you want the symmetry associated with zero mass in the continuum. But right. So on the lattice, if we want to have this symmetry, in order to, you might think you could just shift the sign of this coefficient of the mass term on the lattice. The reason you can't is because of the Gauss law, that for the staggered situation.
In some sense, some interpretation, this is a mass, not exactly as a mass, right? The small a, because it's analog of zero mass, right? What you're doing. I mean, would be
Well, yeah.
So it's like a definition of what means zero mass.
Well, yeah, it's a redefinition on the lattice of what means zero mass. But as you were saying, ultimately we care about the continuum limit as a goes to 0, and so this shift.
Point, especially for two points. Yeah. You see that. So people before did not get it properly.
It's
you could charge them to them.
Yeah, for charge.
Yeah, right. Right.
But one thing that Ross didn't have time to talk about, but if you read the old papers and they develop strong coupling extensions at m lat equals 0, and they all complain that they're really bad, they don't converge to anything. Once you try it at this shifted mass, it greatly affects strong coupling extension, right? Because strong coupling is large. There you see and it works amazingly well, better than you would expect. So I think even for one flavor. For two flavors, it's a very dramatic because you have this shifted mass. The strong coupling vacuum is highly degenerate at the shifted mass and completely non-degenerate at the unshifted.
But you say, for example, the symmetry is so high.
Yeah.
Right.
Yeah.
Yeah.
It has a symmetry which involves shift of theta by pi, which is you go to a different field. Yeah.
Right. Mhm. Yeah, we can talk about either different theories with different values of theta or different vacua or different universes in the same theory with charge n. It's the same idea, right?
So in some of the slide about the derivation of the effective Laplace, so you see the opposite sign as you everyone to be about, right?
Right. It's the sign here we care about. Yes. Yeah.
So it's perfectly set up so we can create the scenario and can we really reason?
That's very possible. Yeah, I haven't thought about that enough to say either way, but
Yeah, they want
Yeah, we were thinking of adding Quark farming.
All of these stories are from the point of view of there's something that I find in the strong functional limit. All these models do exactly what I on the line. And that's exactly your.
I believe so. Yes, we've thought about some of these reductions in the strong coupling limit. Yeah.
I like the electric field, it only takes two values, it takes five.
Right.
It takes five, it only takes two values.
Mhm.
And
Yeah. And yeah, in fact, for in our case, for the two flavor model, we can see that without with the mass shift, we get a 2 to the n degeneracy of the ground state in the strong coupling limit, which
But I think
follows
it's
that.
Heisenberg model, the leading strong coupling limit. I mean, there were some
I mean, for
two flavors.
flavor, yes, I meant for one.
Yeah.
And for my-
I see. Yeah, I can describe briefly. What we do is integrate out the gauge field, so we just have a non-local Hamiltonian coupling, a spin chain for these fermion sites, and then we use a matrix product state ansatz, minimized to extract this ground state. Yeah, it's a one-dimensional. Right, exactly. Yeah, sort of the canonical case. It's a good point. Yeah. So right, DMRG is ideal when you have a finite mass gap and not so much at the critical points. The nice thing about this, I mean, many things can be said, but one thing is that when we do these finite size scaling analyses to get these critical points, this is not exactly where the mass gap goes to zero. We're sort of approaching that point, but on the finite lattice, before we think about the continuum extrapolation, is there still a finite mass gap? And so we expect the convergence to be just fine. That's also true. And that may be related. Yeah. I mean, all of these points, right? There should be a zero mass gap, and so we'd worry about this. But it may be that as we go towards the origin, we somehow need to get closer to that gapless point to really estimate. So that might be part of the problem.
Yeah, so that's part of the correlation.
Say that again, sorry.
How's the correlation that scale?
Right. Yeah. So this is all this is, for instance, a bond dimension of 600 that makes this plot, but we've checked that it changes very little if we take it to 1200. It seems to be well converged. You might worry that we saturate the entropy you could get from the MPS ansatz, but we're not in that regime, so we're safe there.
Yeah, certainly the width of this region becomes extremely narrow. So the only option is it would be exponentially small, like that increase in some functions. Okay, if not, let's think cross again. Yeah, so we'll have a break and
We reconvene at 3:50.
yeah, like
Well, that's not an hour long.
Yeah.
3:50 Central US.
28 minutes.
No, I was also interested in this mass shift.
Yeah.
Because I mean, it kind of reminds me, I mean, if you have an electromagnetic field, so for Wilson fermions, which do have an additive mass optimization generally, right? There is also a non-zero lattice spacing or a non-zero lattice architecture which shifts the mass further. So I was sort of wondering, like, so okay, so if you, I mean, this here comes from restoring kind of the kerosene. That's what you want. So, but if you want to restore chiral-symmetry 4 dimensions for staggered fermions, would you say that something similar can happen, that you should actually shift your mass to some extent as a lattice spacing, or is this just something which is?
We believe it should happen in the higher dimensions as well for U1 H2.
Yeah, I think in that case, everything works cleanly only if you take sufficient number of flavors, because you see, like, for one flavor, the shift relates integer ln's with half integer ln's, right? And that's a shift of theta by pi. Once you go, say, to 2 + 1, then you can't just compensate for it by theta. So I think the analog of what we see for NF = 2 in Schwinger, where it's true symmetry, is we need four flavors in 2 dimensions and 8 flavors. Then it's all clean and there really is a symmetry.
But nevertheless, and even for us, right, like 1 flavor in 2 dimensions, you still see an improvement. You probably see an improvement.
Yeah, we may see, but it's not clear. This shift to, like, ln gets shifted by a quarter or in 1/8, and then there is no, like, theta interpretation for this. Yeah, that's sort of the new thing, but I mean, if you read the old, like, we didn't work on it until a few months ago, but if you read the old papers by Susskind, he always talks about the shift by 1 lattice side. And they somehow, like, ignore this Gauss law being staggered. And there is really an issue there. And, I mean,
we stumbled across this also because we are now doing a lot of, and work on anomalous transport and things like that. And we also use tyrosine.
Yeah, one needs really to be careful about this. Because, I mean, the only paper, like, well, you can look at the new one will come out soon, but the older one, yeah, we also referred, there was this paper by Semenoff and collaborators, which worked in a bit, like, they didn't use integer ln's and stuff, but they were sort of doing something related. But they didn't really identify theta very correctly, I think. I mean, we're doing what everyone was essentially doing numerically, which is taking integer ln's, and there people just somehow forgot that there was staggering of the Gauss law, and there really isn't, like, in some sense, you see this doubling also, like, only for these appropriately doubled fermion contact do you see a true symmetry under the otherwise, it's not.
It's more.
Yes, yeah.
To be honest.
Hey, nice to see you. Yeah, I worry about you are absent. today morning session, so.
Yeah, and my.
Yeah.
Okay.
I just arrived, so I'm still just.
Okay, thank you.
Well, so.
Yeah, just explain. I'm kind of trying to relate about what we did, because for us it was also a lot about basically using the right gamma matrices and lattice. This is also non-trivial, because I mean there's a lot of T staggered how you basically have for gamma pi, for instance, you have to shift in 4 dimensions and so on.
At least the Schwinger model is sufficiently simple that there is pretty little freedom in what to do, like maybe
so,
hard in
in 2D it's not so hard, but in 4D unfortunately, I mean so it is new that if you want to have some remnant accessibility, what you actually do is use this bullshit. But then it's still not completely clear that.
Yeah, I think we looked at it with it, and for NF equal 8, it sort of generalizes like a smaller number of fingers. But that's already something.
No, it's already. You study, so are you always
In the MRT, we extrapolate then on a line
Actually narrows this.
Yeah, I think when we stumbled on this exponential, it's called. Very interesting. Basically, it works. It's much closer.
So what I did is that
George was, I think what he was saying was because he was saying that there were very I mean, that's why when we started expecting lots of you're right, because you know the two operators.
and then I
Yeah, but you see, well, also the fact, yeah, so of course, that's
and we observe that basically.
So then you would just.
Here, I mean, it's like.
So that is and if S is half of integer, so each of the negative sign. And it is enormous, so that so each both if you just log actual computation function many logarithms. Yeah.
You said observe that. It's a pseudo.
Yeah. Right.
Yeah, so you can actually see that.
That's why we were a bit reluctant.
Instead, I mean, if we were like,
There is no.
Yeah, I'll mention it.
I mean, because the idea is also to bring together different.
It looks like
maximally reproduced.
the idea is the thing.
There's this most of the.
Exactly, that's the. Okay, I mean, but I understand.
Yeah, although
Be nice. But I need to back up. Yes, yeah. Yeah, they just had a figure out.
I just improved one policy. So yeah, because your paper saved our paper actually. So we investigated extended Schwinger model, so charge Schwinger model. And so on the massless limit, we also have an exact solution. But without your correction term, we obtained some discrepancy from the theoretical prediction. So we have more than 2 months discussion about this discrepancy. And then your paper appear on archive, and we find the yeah, perfect consistency with theoretical. Thank you very much. I'd like to say that. Yeah. Yeah.
So this is just for one flavor, which are
This is
cute,
one
right?
flavor. Yeah, it's already published. Yeah, I think the second paper.
Yeah, we did see your.
Yeah, but anyway, thank you very much.
Who would think that Abelian Schwinger model and find something?
Yeah.
That's where we actually worked for a long time trying to match this decoupling and strong coupling expansion and finding weird things. And that's part of the reason. Yeah, we weren't at first looking at the chirals. But the old papers have really a lot of very strange things.
That's
Like the even the strong coupling expansion or but Hamer spent many years working on this on these comments. Because his extrapolations are really bad. Seems like there were.
Oh, yeah. That's really the good part of it. I mean,
Oh, but then these people.
Yeah.
Well, maybe, yeah, I wouldn't worry about making the extrapolation like industrial. Exactly, yeah. I mean, obviously it gets harder as you get into smaller. Yeah. But this is agree that it should be hard.
Oh, yeah, okay.
Exponential small.
Like 4 times as long.
Okay, so maybe your publishing is
Yeah.
is warranted. Yeah, yeah. Oh, yeah.
Yeah. Yeah, I'll put this view breaks on it.
Oh, was this new?
Well, it's not that new, I just started working on it.
I see, okay.
I think it's just the right route to present. That they actually care about.
That's right, yeah. Oh, thanks a lot.
I'm curious about, I don't know if you have time, but about the things on them. So you integrate out, you get some PJ.
Sorry.
Yeah, sorry. We talking.
Sorry. Yes, so. Right, so the Hamiltonian has the sum of the electric field squared. But these electric fields, right, by the Gauss law, they're related to the electric field at the beginning of the chain, plus all these fermion charges.
Okay.
So then that sum of electric field squared can be rewritten as a non-local interaction between all the fermions.
Okay.
Via the Gauss law. And so right, so at that point, then it just becomes a theory of and spins with a non-local Hamiltonian.
But they are Fermi then.
Well, yeah, by a Jordan bigger conjugation.
Okay.
I think either way, honestly, put it into the MRG, but we have to look
Okay.
at the spins, but yes, either way.
And then you put this, so each label here is pin up to down.
Right.
And how many do you put in the matrix? These are matrices.
Yes, so we have bond dimensions of several hundred. And
Okay.
yeah.
And do you use some special program? Like,
Yes, there's a wonderful program for this that almost takes away all the work. It's called iTensors.jl.
in Julia?
In Julia, yeah.
Oh, yeah, we're trying to use it, yeah, okay, and can you then put some parameters and minimize?
Right, yeah, it does almost all the work for you. What you do is tell it the Hamiltonian, and then that's really it. And then you just give it a random initial state and we'll minimize that to lowest energy. You can even do higher states if you want. And then, you know, if any operator you can write as a matrix product operator, you can take its expectation value in that ground state.
Yeah, I was trying to learn that iTensor. Yeah, but the thing is, I wasn't sure the people are using it, so you want to learn something. Nobody uses it.
Right, sure.
Some guy convinced me to use Julia, and then I said, maybe I'm the only one doing it.
It's the
Okay.
only thing I use Julia for.
No, I use it because I use this, what is it, the convex maximization. Some guy told me about the maximization program that only works in Julia.
I see,
Then
I
say,
see.
okay, I have to learn.
Right, yeah, that was my case as well with iTensors. Yeah.
Okay, but thank you.
Proved worth it. Yeah, thank you.
Okay.
What mentioned before, what mentioned project cannot mention in the dance.
So this needs to be improved.
So the question is basically.
Can you use your own computer here? It's quite good.
This is mine, yeah.
Okay.
Yeah, they have all kinds of connectors, so
Please be gentle. Okay? Be gentle.
with the
With us, with us.
or not breaking. I thought, yeah, I was worried already to break it.
Okay, well, welcome back for the last talk of today. It's been a really nice day here. And Martin Kruczenski will conclude with his discussion of positivity and the loop equation.
Okay, is the microphone okay? So first I wanted to thank Alexei, Igor, and all the other organizers for the opportunity to give a talk. And I'm gonna start, before I start the talk, I want to discuss an idea that is gonna be important for us. And it's in physics and mathematics, there are structures that, as we know, are, we can call them rigid. For example, a crystal, if I have a crystal, I know the position of some atoms, I can know the position of all of them. Integral series, analytic functions, if I modify an analytic function at one point, I have to modify it everywhere. And these structures can be determined generally from general constraints many times, or at least approximated. And the interesting constraint we're going to consider for this talk is positivity. In particular, we will have always some matrix that is positive semi-definite. Standard examples are if I have the correlation functions of some random variables, xi, and I multiply this matrix by xi, xij, where this is an arbitrary vector, I get the expectation value of the square of something that has to be positive for any xi. And by definition, that means that this matrix is positive semi-definite. And again, if I have a matrix time its dagger is positive semi-definite, the matrix of scalar products. And in other situations, if I have a probability measure or any positive function and integrate a positive polynomial, will be positive, and that gives rise to this momentum or properties of the moment of this distribution. So what I'm going to try to use is this type of positivity in lattice gauge theory. I'm going to describe the single plaquette model or unitary matrix model and lattice gauge theories in 2, 3, and 4 dimensions. And the idea is that this positivity allows a formulation of the theory purely in terms of gauge invariant quantities, as I'm going to discuss. And then I'm going to define other cases that were already presented. Actually, Yuan Xing gave a very nice talk this morning, and perhaps I'm giving the boring version of his talk. So what do we do in lattice gauge theory? So I'm going to describe this older paper we wrote. And then I'm going to mention the new results of Kazakov and Zheng that improve very much in what we did and makes this more realistic. And the motivation, as I said, is can one define a gauge theory purely in terms of gauge invariant quantities? ADS-CFT gives a possibility in terms of a string theory, but I want to consider the most standard version, which is, can we define it as a theory of Wilson loops? And the idea was to use the Migdal-Marchenko loop equation. And if you solve the loop equation, then you have an expectation value of the Wilson loops without any reference to the gauge degrees of freedom. However, what I'm going to argue is that the loop equation generically has infinite number of solutions, and the positivity condition is what chooses the correct one. So let's start by the single matrix model. So I have a unitary matrix with some action, and I want to compute this integral. Moreover, I want to compute the same integral with trace of u to the n. Normalize these matrices are SUN matrices with capital N. And this W little n I'm going to call the Wilson loop. And I want to compute these quantities without doing this integral. And this was done by Gross and Witten in the 80s and by Badia using analytical tools with the spectral density, by Friedan using the loop equation. And later, Marchesini, for example, described a numerical method that it didn't work so well, but it was good for us to motivate us in this work. So the exact solution has a third order phase transition at lambda equals to 1 for the expectation value of the plaquette or the just u, the trace of u, which is the energy, basically. So if you do a change of variables in the integral and say that the integral should not change, one gets a Schwinger-Dyson equation or equation of motion, and this gives a recursion equation for these expectation values. So if somebody gives, well, W0 is just 1, W1 is what we would like to compute, but I don't know it, then I can compute W2, W3, and all the others. But the question is, how do we get W1? And if one puts W1, and that's the recurrent relation, one sees that for some values of W1, the recurrent relation blows up. And this has to be bounded between -1 and 1, so that value of U is not good. But can we do that more precise? And what we argue is the following. Suppose you have a linear combination of these matrices U to the N. These are arbitrary complex coefficients. With BB diagrams, we said it's positive semi-definite, so I take the trace, just that should be positive. And the mean value of a positive quantity is positive, and these are unitary matrices, so this is U to the power of N minus M. The expectation value is W N minus M. And that means that if I arrange these expectation values in these diagonals, this matrix should be positive definite wherever I stop writing this, because these coefficients were arbitrary. So that means that I put this 1, I put this U, and all this I put from the recursion relation, and I check if this matrix is positive definite or not. And if I put 4 by 4, I get that U has to be in this region. If I put 6 by 6, it's here, and 8 by 8 is almost equal to the exact solution of Gross and Witten, which is here. And if you do, you can do much bigger, and then you don't distinguish it from the exact solution. For example, you can do similar things as I'm going to describe later by Hermitian matrices. That's one very nice paper by Henry Lin. In that case, U dagger is U, so you get N plus M when you write this matrix. But yes, sorry, I should mention, thank you very much. All that I'm saying today is in the limit of N goes to infinity. So I'm not going to say anything about finite N. Yes, sorry about that. And in particular, here you get the expectation value of this product. And because of the large N, it factorizes in the product of expectation values. And there are also extra terms on the right-hand side that go away. Yeah, thank you. Sorry about that. And one can write an effective action, for example, in the 2 dimensions, in this case, for a single matrix model, which is an effective action for the Wilson loops. And if you minimize this action, you immediately see that you get that all the W's are 0 except W1, that from here, when you minimize, you get 1 over 2 lambda. That's the strong coupling result. But the weak coupling result does not appear unless you minimize the action with the condition that this, sometimes called Teplitz matrix, which has this organization of the diagonals, is positive semi-definite. This semi-definite programming problem can be solved with many different types of software packages, and is pretty standard. And the constraint, as I just showed, appears at weak coupling. I think Vicky emphasized also many long time ago that the Jacobian of the change of variables from the U to the W's should be positive, and so there is always some positivity in all the formulations. So in lattice gauge theory, I'm going to consider 2, 3, and 4D, but I'm going to draw just the 2D. So we have in each link of the lattice a SUN matrix, and I have a plaquette, which is just this square. And if I multiply these matrices and I take the trace, that's the action, sum over all plaquettes with all the orientations. And a Wilson loop is a closed path. So I multiply the matrices associated with each link. I take the trace and I put it inside the integral, and that's the expectation value of the Wilson loop. And we want to compute those without doing the integral, once again, in the large N limit. And this can be done in Monte Carlo. Some results, well, this is exact. As I mentioned, well, I should say in 2 dimensions, by correct choice of gauge, you can reduce it to a single plaquette model. So that's the 2D case of Gross, Witten, and Vadia. In 3 and 4 dimensions, you can do Monte Carlo. For example, Tepper and Postrini found a large N, well, like for enough N, there is this phase transition 3rd order and 1st order. Okay, so what's the loop equation? As I said, this was associated with Bigdal and McKenko, although Eguchi, Förster, Vadia, I think, and many other people discuss this type of Schwinger-Darwin equation associated with one link. So I have a link of the lattice, and I do a transformation of that matrix, and I say that the integral should not change. And what you get graphically is that you take some Wilson loop through this link, and you replace it by making a little curl, minus making the curl the other way, that gives you like this kind of hook. If the loop goes twice or more through the link, you get to split this loop in two by interchanging the entrance here, and you get two Wilson loops that factorizes in the large N. And as Eric was saying, and then if you put one loop one way and it goes the other way, it also factorizes, but in this, you close it here, and this goes with a minus sign. So once again, the loop equation has a linear term from here, has the same Wilson loop, and if it goes through a Wilson line twice, you get a quadratic term like before. Here I just separated the plaquette, but you can write it like this, and that's good for any action that is written in terms of Wilson loops. So instead of contracting with a plaquette, you contract with a rectangle or whatever other loop you have in the action. So how do we solve this? Well, we can enumerate the Wilson loops, like the square, the rectangle, the chair, maybe you call it, and some other. You make a list. It's a big list, but fits in the computer, and then you write equations for them. And we try to solve this equation. And we have the same but worse problem as in a 2D or single matrix model, which is that if I write the equations for Wilson loops, let's say up to length 12, I will have like 5,000 equations, but this will involve loops with length L plus 4, and that means that there will be like 4 million variables. And that obviously there will be a lot more solutions for that. And if I keep increasing L, that keeps getting worse because the number grows exponentially. So there is an infinite number of solutions. So how do we choose the correct solution? Well, we need to impose some positivity. What do? Well, we take, let's say, 2 points of the lattice, and we take a set, we choose a set of open paths from one to the other. Now, given the configuration of the lattice, for each open path, I multiply these matrices, and I get a matrix for this path, for this the green path, the purple, the black, and then I make a linear combination of those matrices with arbitrary coefficients. I say this is positive, but now these don't cancel because they are usually, unless L is equal to L prime. What this means is I go along the path L prime, and then I come back along the path L. That means that this trace corresponds to a closed Wilson loop going along L prime and coming back along L. And when I take expectation value, this should be positive. So that means that these are Wilson loops. If I organize the expectation value of Wilson loops in a matrix, that matrix should be positive definite. So not only should these numbers obey this equation, they should obey that put in this matrix is a positive semi-definite. Now, if I normalize this with L, the trace is this matrix is 1, so it's positive semi-definite, the trace is 1. I can think of it as a density matrix. So I may be curious what happens if I take the compute this entropy. And this entropy is the information you lose by taking the trace over the color indices. And so this is an entropy that I can define again purely for the Wilson loop. So if you give me the expectation value or whatever numbers the Wilson loops are, I can compute this here. So it has some sort of physical interpretation. And if I, instead of trying to compute the Wilson loops with the loop equation, let's say I use the Monte Carlo, I compute this entropy. You see that this entropy that only involves the Wilson loops has a jump at the phase transition that you have in 4 dimensions. And this is a large temperature regime. The entropy is large, and this is large temperature. There is no temperature here, but lambda can be thought as a temperature, the coupling. So when lambda is large, you have random matrices, and when lambda is small, you have matrices all close to identity, and the entropy is very low. Well, I choose this and this and this. I choose different ones. And all seem to have very similar entropy. These are the different colors. So it seems to be somewhat independent of what initial and final points we choose. Ideally, you choose all of them and you get the more constraints. But we saw that just choosing, we usually choose this and take enough open Wilson loops that give some good constraints. But you could add more. Yeah. Usually you have a bunch of matrices that they should be positive semi-definite. Now there is a very interesting thing, which is what happens at the boundary of this space. So the matrix should be positive semi-definite. So the boundary is when one eigenvalue becomes 0. Then after that, it will be negative. So let's call C0L the eigenvalue. So if I compute this, that should be 0 by definition of 0 eigenvalue. But if we go back to this definition, we have that this with expectation value is 0, but the expectation value of something that is always positive is 0, means that it's 0 for every instance. And that means that this is 0, but if the trace of A dagger A is 0, then the matrix A itself is 0. And that means a very curious property that this matrix with this particular coefficient is 0 for any configuration of the lattice allowed by the action. And that means that a particular linear combination only at the boundary of the space. A particular linear combination of open Wilson loops vanishes. And that if I close it with another arbitrary Wilson loop, I get a linear equation for all Wilson loops. For example, one can show that if the plaquette is 1, all the Wilson loops are 1 using this, so that's the free theory and things like that. So I want to mention the solution by Marchesini that he said, okay, instead of, well, he said, let's close the recursion relation by setting some Wilson loop very large, L, to 0. And if you do that, you get the polynomial equation for U because all the previous loops are polynomials of U. And you get this very funny shape, which is, you get the good result for a strong coupling if you choose the lowest root, but here you get something funny. But he was satisfied that when L is large, you get the lower boundary seems to be the correct solution. Sorry, this is the coupling, and this is the expectation value of the plaquette. So energy as a function of coupling, it should be 1/2 lambda here, and it should be 1 minus lambda over 2 here. And there is a phase transition at 1. Yeah, sorry. But essentially, we need to reproduce the red curve, which is the exact answer, and the blue curves are the solutions of the polynomial. But this clearly motivates us that, okay, there is a problem, we should be able to do this better. And if you look at the analytic solution, it's important that the spectral density is positive because it's the number of eigenstates in a range. So we said there has to be some positivity condition, and that's how we found that positivity condition that seems to work. Okay, so this is a 2D. As I said, it reduces to a single matrix model. So let's consider 3D. 3D, these red dots are Monte Carlo results. These black are perturbative calculations, so we can ignore. And this is by the upper bound and the lower bound by taking a larger and larger Wilson loop. So you approach this, the weak coupling, it seems to be very close to the upper bound. So that means that you have these 0 modes. And here is kind of in the middle, although it seems to be closer to the lower bound. And in 4D, you get similar thing. The QCD is here because the lattice spacing lambda should be small because of asymptotic freedom. So here is where you should look at the continuum limit, and we didn't do that. But I would like to believe that these 0 modes that appear here are somewhat related to that, but I don't know how that works. The other thing is that here you would like to compute large Wilson loops and show that they obey area law, and we are only computing the plaquettes, they say. We are not computing large Wilson loops yet. These are just numbers that show that good agreement between our method and perturbation theory and Monte Carlo. One thing I want to emphasize is that these are strict bounds. So although you evaluate them numerically, it's strictly true that the expectation value of the plaquette, once again, this expectation value of the plaquette versus coupling, they are all the plots like that. And this is a strict bound. Although you evaluate the bound numerically, it's strictly true that this matrix is positive definite, and if U is somewhere here or here, it's no longer like that. So it's not a numerical simulation, it's a bound that you evaluate numerically by some computer program. And then that's what we did, and we were kind of happy, but more or less. But then Kazakov and Zeng, like last year, came up with a much improved numerical approach where they put more constraints and also tackle some of the nonlinear part that we ignore. And okay, I'm not going to describe too much, but they say they improved the method, and now one can say that the 3D is almost there. I think they have a much better lower bound that goes to 1. And with some more effort, one can believe that indeed this method converges to the Monte Carlo solution. In a strong coupling, the hacks much more the upper bound, the Monte Carlo solution, all the way up to here. So these clearly things I would claim that there is good agreement with the Monte Carlo just from this method. Let me argue that this method is just strictly large n. The computations are done using the Migdal-Marchenko loop equation and the positivity condition. So it's purely Wilson loop calculation. There is no matrices, SUN in anywhere. And so it's completely independent. So it's not related to the lattice simulations. Nevertheless, it's the same system, but we find they found a good agreement. And as I said, we still need to compute larger Wilson loops. So a few random comments. One is that although all this is done with the computer, one can analytically write small matrices. And for example, one can put bounds in the difference between arbitrary Wilson loop and the same Wilson loop with an extra plaquette. At small coupling, this U is close to 1. So this is something small. That means that the Wilson loop don't change very much. And since you can construct any Wilson loop by adding plaquettes, you get bounds which are not that good, but bounds on any Wilson loop. You can also see that there are arbitrarily long Wilson loops that you may think, okay, the matrices are random, so she should be 0, but they are not. They are very close to 1. So you can get this bound. When U is close to 1, this is a little less than 1. So there are arbitrarily long loops with expectation value is 1. But they don't have big area. They have big, like, well, this maybe I will skip, but this is just to mention, if you are familiar with lattice, in lattice, you have a configuration, you want to compute a Wilson loop, but first you smooth out the lattice configuration to reduce the noise. And one way to do that is what's called gradient flow, that you take some sort of average. But if you look, it turns out that this method to take the average uses the exact same operator that appears in the loop equation. So we didn't write this anywhere, but just an observation that if you flow the Wilson loop, so you take the Wilson loop of the original configuration and of the smoothen out configuration, it's just related by solving this equation. In the larger limit, we can drop this. So the smooth out Wilson loop is just some exponential. T is arbitrary parameter that determines how much you are smoothing out of the initial Wilson loop. So this smoothen out Wilson loop should obey also a loop equation. That is more complicated because the self-intersection, because you are basically decorating the Wilson loop with curves everywhere. It's more, so I don't know if this is tractable, but you get a flow loop equation. But the one thing I want to emphasize is that these flowed Wilson loops are computed in smooth out configurations, and therefore doesn't matter what if it's smooth out or not. If you compute it for a configuration, it should obey the positivity conditions. So the flow Wilson loops should obey the positivity conditions. That means that this exponentiation on this may give more constraints. I don't know. So these are just comments. So now I want to, I guess that's more or less what we did and Kazakov and Zeng did. And now I want to describe some other work that was already mentioned this morning, and I have nothing to do with the rest, but it helped me understand more how this method should work. One is the Ising model. It has no large limit, anything, but it has equations by flipping the spin. It's like the Dyson-Schwinger equation and has some reflection positivity constraint. And the Xi group at Harvard and Barak Gabay is here, so you can ask him more because it's very nice work. They computed for 2 and 3D IC models, so I'm just showing 2D, the expectation value of the magnetization as a function of the coupling. One can see once again in this region, you get the upper bound agrees with the magnetization, and here you need to do more work, but it's converging. And this is also the correlation between the spin and the neighbor, and it's also converging very nicely to the exact solution. So I think it's quite surprising that one can still say new things about the IC model. But yeah. Then Herring-Ling, some very nice work, show how to solve Hermitian matrix models with this type of numerical method. Let's consider one, as he following his paper, one matrix model which has quartic interaction and quadratic. M is Hermitian now, and I want to compute these WNs, the expectation value of trace of M to the N without doing the integral. And once again, in the large N limit, I need to, I can write, just modify M by a little bit, say that the integral does not change because it's a change of variables, and you get this loop equation. And if I do this linear combination, I get that this matrix should be positive definitely. Now this can be solved exactly, so he compared the exact solution and saw that the bounds converge very fast to the exact solution. Once again, if you put too many, you just don't distinguish the exact solution from the known one. But okay, he did this for 2 matrix models, and Kazakov then applied this to other models where you do not have any exact solution, and they found solutions for those that you can compare with Monte Carlo. So that's a very interesting here. And then I want to mention something related with dynamical systems, because at the end there will be some interesting result. This was done by Galushkin previous to what we did, but I learned in a talk from Xi. Well, if you look, it might not look similar, but he showed at least how you can make it very similar to the type of things. Yes. Oh, sorry. To the type of problem that we are discussing. So this seems something very different. So I have a dynamical system. You can think of X as position and Y as momentum. Let's say we have this P dot is equal to this, and this is called sometimes the Bogdanov, at least some reduced version of the Bogdanov system. So I'm following what he showed in the talk, but I'm taking these calculations done by a student at Purdue for this particular case. So suppose I have this system has periodic orbits in position momentum. This is X and P, sorry, and Y, but Y is like P, and then I have some unbounded orbits. Let's say I take a periodic orbit and I average over a period, X to the N, Y to the M as a function of T. And I want to compute these numbers without solving the differential equation. So how do we do that? Okay, we take some f x to the p, y to the q, take the time derivative, and that's p x p minus 1 x dot, but x dot is y, so I get y q plus 1, and the same with the y dot. And now f is periodic because it's x and y are periodic, so if I take time derivative and average, I get 0, and I get this equation once again. So I get one equation for these w's, which is once again a recursion relation. That given the initial ones, you can compute the other, but what are the value for initial value for the iteration? And once again, we can do something very simple. We can take linear combination with arbitrary coefficients of x to the n, y to the m, all squared. That should be positive. And it should be positive if I average over an orbit, periodic orbit. But then this thing is just by definition the w n plus n prime, n plus m prime. And this is positive for any coefficients a and m. So if I consider this composite indices nm, n prime, m prime, then this matrix should be positive semi-definite. And suppose I want the, like, I don't know, in some sense, the tallest periodic orbit. I can try to maximize W02, that means average value of y squared. And I maximize this with the condition that the recursion relations are satisfied. and this matrix is positive semi-definite. And you get the value, and this you can compare with what you get from the differential equation, and it's the same. But now there is this is the thing I want to show because I found very interesting. As I said, I learned it from Xi is that now we say, suppose we are at the maximum, so at the boundary. At the boundary, we have a zero mode. We have a zero mode of this matrix. A zero mode of this matrix means that if I multiply this by the zero mode, A and M, I should get 0. So this should be 0. But again, this is the average of something positive. So this should be 0 without the average. But if this square is 0, this should be 0. So for the particular A and M, this should be 0 for any X and any Y. And that means for any T. That sounds strange before with the use. But here, what's this? Okay, if I have an equation that should be valid for any T, this is just the equation of the orbit. So if you look at the 0 values of this, you indeed get this shape of the orbit that has the highest Y square. So we got the physical interpretation for the 0 mode. Would be nice to understand better what it is in the other models, but all this allows you to use physical interpretations in one into the other and so on. Okay, so I'm basically done. So to conclude, this positivity can be used with great effect in many different systems. It's reduced to the problem of maximization of linear functions in convex spaces. We did it for the lattice gauge theory, and I would like to argue that using the loop equation of Nidal and Markenko plus this positivity, you get a well-defined formulation of the lattice gauge theory for the Larsen limit, purely in terms of Wilson loops with no reference to the gauge degrees of freedom. But other people use this for other, I mean, not necessarily our thing, but the same type of idea for other systems and obtain some very important results. And all these results are again rigorous. They are not numerical simulations. They are bounds obtained, compute numerically, but they are strict bounds. And the general picture is that you have some quantity that has some recursion relation, allows you to compute all the values, but you need to know the initial or starting point of the recursion. And the way to find those is to know that this whole set of quantities has to obey some positivity constraints, and therefore you cannot choose the initial values randomly. Okay, that's all. Thank you. Oh, yeah.
Correct me if I'm wrong, they're not physical. They would fail, for example, with the theta.
They will fail what?
With the theta term, because the expectation value.
Well, this is for the Purian, this is for, well, no, I don't see how they can fail. These are true for, so if I have a links, and in each link I put a matrix, and I don't care what the action is, and my claim is that this matrix is positive definite because of just this. It doesn't depend on the action.
Does theta term give them high in your?
I mean, it has a weight.
Because it's complex.
Yeah, exactly. So the average there, even though the average is not guaranteed to be positive. And because the measure is not.
Okay. Well, yes. No, this is if you have. Okay. Well. Well, Kazakov, Zheng, they also added reflection positivity to the equation, but well, yeah, well, just not putting any, yeah. So if the measure is not positive, then this doesn't work. You know. Yes. So there is some idea that is you have the same problem in Monte Carlo, then maybe this also doesn't work. I don't know. Yeah. That could be. Yes, that's true.
I think David wanted to.
No, that will be nice. Yes. So The only thing we were not sure, but the thing we see is that, well, here it converges, and using the analytic method that you use, I guess you know that the solution is unique. But in these cases, yeah, well, the numerical evidence is this is converging, and now is. Yes, so in this case, there is only numerical evidence, there is no rigorous proof. In the 2D, you know the exact answer, so you can, I guess, use that. That's what Friedan did. No, Friedan did it analytically, but it's just, how is it? Well, okay, Friedan did. What you do, you write sum of some complex number z to the n, w to the n, that's the resolving of some analytic function. Obey some equations from the loop equation, and then you can see that this positivity is equivalent to the positivity of the spectral density, and you find a unique solution. So that's but that only works if you know the exact solution. If you, or there is a way to find the exact solution. For that will be very nice to show that this in 3D, for example, or 4D, this will converge to a unique answer. And we don't have any proof like that. It will be nice, yes. It will be an important part of the method.
Thank you.
Yes. So I show one plaquette and I want to. Yes, so. Well, it gets harder. Okay, I don't know. So suppose I have a Wilson loop which is larger, like 2. Yes, then the bounds are, you get bounds, but they are more loose, so you have to work harder. So for us, we did try to do a rectangle, and it was close to the numerical result, but not much. I don't know what they obtained for that. But yes, so the important next step is to be able to compute also larger Wilson loops. Implicitly, you can do, for example, expectation value of plaquette, expectation value of 4 plaquettes, and plot an allowed region. But we didn't do that. Nobody did that yet. But that's an important thing if you want to go to understand quark anti-quark potential or confinement or things like that. You need to compute larger Wilson loops, and we don't know how to do that. So in principle, here we get all the Wilson loops because we solve the equation, but they don't have the correct values. The bigger, the worse it is. Yeah, okay, assuming that is positive. I guess that was that caveat that I didn't understand but before, but yes, so you just put some matrix here. And as I say, assuming that the measure is positive, the positivity of this matrix is independent of the action. But then the question is that it gives some interesting results. For example, this is always positive, and it does not depend on the action as long as the action is positive. So you can conclude that this is true for any action.
But the reason it's probably on the slide, but the reason I'm asking is that I thought the location of base transition can depend on the lattice.
Oh, yes.
It is go, but if you use like a key kernel action,
yes. So the actual values. So this is a range, but the actual value of this depends on the action. But no matter what the action is, you have this range. Yes. The loop equation, indeed, the loop equation is the action basically. So the loop equation is the action. So it's essentially if you write the action in terms of Wilson loop, like I did plaquette, you can do rectangle, others. You just intersect them with your Wilson loop, and that's the linear part. So this equation depends on the action. That's the dynamical information. The other is kind of kinematical if you want, but it's important.
Okay,
Find an action where these equations are simple, we still have a direction.
Yes, so people used to usually put actions to have more rotational symmetry, but I don't know, yeah, what you are saying, I didn't think about.
External action.
okay, maybe we can postpone further questions and then a long day. Let's thank.
Okay, thank you.
Resume tomorrow night.
That'll be easy. Thank you for your talk. That was very interesting.
Yes, I didn't know because why did they cancel the flight?
Well, you can bound the chain. So I have an expectation value of some weak loop, and then I add a bracket, and I have the expectation value of that, and I ask for the difference. And that difference has a bound. And that's what I know. Oh, not that good, but yeah, it's just to show the one. So if this, so all these are bounded by 1, so this is 4, let's say, and this is 1 minus u. So when you are in the close to the free theory, so when you are here, u is close to 1. And that means that this difference is small. But if you have the strong capping, which is not that important sometimes, but then the difference can be large. So are we capping? This will be 1 minus u to power how many plaquettes you need to go from one to the next. And this is a 4, I guess. Yeah, I'm not sure I could do anything with it, but I just wanted to show that it's possible just by writing by hand, or you don't need a research computer.
Why do you say this?
I know these are all less than 1. Yes, but this could be, I think they can be negative.
Yeah, you know, I mean, it went on but I thought it would be nice to, you know, either you or Rob, like, start us on something ground.
But worst case scenario, this cannot be bigger than 4. Even, yeah, so this modulus of this is less than the sum of the modulus, and that's less than 4. Yeah, it could be smaller. Yeah. Well, this is, but this will be already 2. So these are big. If they have big area, they are probably very small. So this will be 2, but 2 and 4 for this purpose is already the same. But this is the thing that this is.
Okay, so the
Yeah, so
the main point is this.
Yeah, when U is close to 1, this is difference is bounded by something small. But when if U is 1, that these are unequal, and that's the free theory. So you can see that the only theory that has U equals to 1 is the free theory. I mean, maybe that's trivial, but you can see type of things like that.
It'd be nice to have a bound on the other side. Like this, yeah.
On the what side?
And
This big.
on the other side.
Why do you
A
want
lot
that?
lower bound. Because you see, with this kind of expression in principle, you can estimate the
Yes. But you want, but they thought well, okay, you have bound on both sides and they are close, then you can, you have the value. Yeah, that's your